something is wrong. Not in the way that a calculation is wrong, or a theory is incomplete, or a measurement needs refinement. Wrong in a deeper, more unsettling sense, the kind of wrong that sits at the bottom of your chest like a stone you cannot identify, a weight you did not notice until you stopped moving. Something is wrong with the picture of reality that science has spent centuries carefully, painstakingly, brilliantly constructing. And the most disturbing part is not that scientists have discovered this. The most disturbing part is that they cannot explain it. Not yet. Maybe not ever. And the closer you look, the more you realize that the cracks are not small. They are not cosmetic. They are not the kind of imperfections that get smoothed over in the next edition of a textbook. They are structural. They run through the foundation. And the foundation, it turns out, may not be as solid as anyone believed. You have probably never thought about the moment when you stopped questioning reality. It happened gradually, the way most fundamental shifts happen, not with a dramatic announcement, but with a slow accumulation of explanations that started to feel like facts, and facts that started to feel like the ground beneath your feet. At some point, the universe became a known thing. Not fully known, of course. Scientists have always been careful to say that, but known enough, understood enough, mapped enough that you could look at the night sky and feel, somewhere, beneath the wonder, a quiet confidence that someone somewhere had worked out what all of it meant. That confidence is what this is about, because it is cracking. And the crack started with something that, on the surface, sounds almost too mundane to matter. It started with a number, a measurement, a reading from a telescope pointed at a galaxy so far away that the light you are receiving left before the Earth existed. Scientists were trying to measure how fast the universe is expanding. A question they thought they already had a rough answer to. They had models. They had predictions. They had decades of data and generations of brilliant minds who had poured their lives into understanding the large-scale structure of the cosmos. And then, the measurement came back wrong. Not slightly wrong. Not within the margin of error. Wrong in a way that, if you understood what the number meant, would make your stomach drop. Because the universe, according to this new measurement, was expanding. Faster than it should be. Not just a little faster. Significantly faster. Faster in a way that contradicted not just one theory, but the entire interconnected framework of modern physics that we have been building since Einstein first bent the concept of space-time over a century ago. To understand why that number matters, you have to understand what it means to build a model of the universe. Imagine you have never seen the ocean, but you have studied it your whole life. You have analyzed water, samples. You have built mathematical models of wave behavior. You have calculated the pressure at different depths. You have predicted with extraordinary precision how the tides move based on the gravitational pull of the moon. You have never seen the ocean, but you know it. You trust your models because they work. They predict things before you observe them, and when you observe them, they match. That is the beauty of physics. That is what makes it different from opinion, from belief, from guesswork. It predicts, it verifies, and when the prediction and the observation agree, you have something that feels like truth. Now imagine that one day, someone goes to the ocean and measures the waves, and the waves are moving faster than your model says they should be, not because of a storm, not because of an error, but simply because the ocean is behaving in a way your model did not anticipate. That is the Hubble tension, and it is keeping physicists up at night. The Hubble constant is named after Edwin Hubble, the astronomer who in the 1920s gave humanity one of its most disorienting gifts, the discovery that the universe is expanding. Before Hubble, most scientists believed the universe was static, eternal, unchanging on the largest scales, the same today as it had always been and always would be. Einstein himself, when his equations of general relativity predicted a dynamic, expanding or contracting universe, added a fudge factor, what he called the cosmological constant, just to make the math produce a static universe, because a moving universe seemed too strange to accept. When Hubble's observations confirmed that galaxies were moving away from us, and that the farther they were, the faster they were receding, the cosmological constant was quietly abandoned. Einstein reportedly called it his greatest blunder. The universe was not static, it was growing, and that growth had a rate, a measurable, calculable rate that came to be expressed as the Hubble constant. For decades, the precise value of this constant was debated, refined, and slowly pinned down. By the early 21st century, two independent methods of measuring it had been developed, each built on completely different physics, each representing the best of human ingenuity and scientific precision, and they disagreed. The first method looks outward. It observes the cosmic microwave background, the faint radiation that permeates all of space, the afterglow of the Big Bang itself, left over from the moment the universe cooled enough to become transparent to light. This radiation is ancient. It carries information about the state of the universe when it was only about 380,000 years old, in a cosmos that was still a roiling plasma of energy and matter. By studying the subtle temperature variations in this background radiation, physicists can reconstruct the early universe with extraordinary precision and, from there, calculate how fast the universe should be expanding today. The second method looks at the nearby universe. It uses a chain of distance measurements called the cosmic distance ladder, starting with variable stars called Cepheids, whose brightness follows a predictable pattern, then extending to type Ia supernovae, which explode with such consistent energy that astronomers can use them as standard candles to measure vast distances. By combining these measurements, scientists calculate how fast distant galaxies are, moving away from us right now. Both methods are rigorous, both are reproducible, both have been checked, rechecked, refined, and improved by teams of researchers who dedicated years of their careers to eliminating every possible source of error, and they give different answers. The early universe method gives a Hubble constant of around 67 to 68 kilometers per second per megaparsec. The nearby universe method gives a value closer to 73. That gap, that roughly 8% discrepancy, is not a rounding error. At the level of precision these measurements have achieved, it is a screaming alarm. You might be tempted to think that 8% does not sound like much, and in everyday life it is not. An 8% difference in the price of groceries, in the length of a commute, in the temperature on a summer afternoon, none of that would register as catastrophic. But in physics, when two independent methods that should be measuring the same thing give results that are 8% apart, and when both methods have been cross-checked by multiple research teams using different instruments and different techniques, and when both results keep getting more precise rather than converging toward each other, that 8% becomes one of the most significant unsolved problems in all of science, because it means one of two things. Either both methods are somehow flawed in ways that have not yet been identified, which would represent a catastrophic failure of our most sophisticated scientific tools, or the standard model of cosmology, the theoretical framework that describes how the universe was born, how it evolved, and how it behaves, is missing something fundamental, something we do not understand, something that is, by definition, beyond the current edge of human knowledge. And here's the thing about the current edge of human knowledge. It is not where most people think it is. There is a popular image of science as a frontier, a line advancing steadily forward, pushing back the darkness, converting unknown into known. In this image, the unknown is simply what we have not gotten to yet. It is just a matter of time, of better instruments, of more computation. The known grows, the unknown shrinks. Progress is linear, but that image does not capture what is actually happening at the deepest levels of physics right now, because the edge of human knowledge is not just the limit of what we have discovered, it is, increasingly, the limit of what our frameworks can contain. It is not just that we do not know the answers, it is that we are beginning to suspect that we may not even be asking the right questions, and that is a very different kind of unknown. To feel the full weight of what that means, you have to go back further. Back to a time when physics felt like it was approaching something magnificent. Not just the next discovery, but the last discovery. The theory of everything. The equation so fundamental that it would contain, in compressed mathematical form, everything that exists. The dream of a unified theory of physics is not a new one. Newton's laws gave humanity the first taste of it, a single mathematical framework that could describe the motion of a falling apple and the orbit of a planet with the same equations. That moment, when Newton realized that the force making fruit fall from trees was the same force keeping the moon in orbit around the Earth, was one of the most profound conceptual leaps in human history. Gravity was not just a terrestrial phenomenon, it was a universal one. The same rules applied everywhere. The universe was lawful, and if it was lawful, then in principle, it was comprehensible. That confidence, The confidence of a lawful, comprehensible universe is what powered 3 centuries of scientific progress. Maxwell unified electricity and magnetism into a single framework. Planck, Einstein, Bohr, Heisenberg, Schrödinger, and Dirac built quantum mechanics, the theory that describes how matter and energy behave at the smallest scales. Einstein's general relativity described how mass warps the fabric of space-time, generating what we experience as gravity. The Standard Model of particle physics cataloged all the known fundamental particles and 3 of the 4 fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force, into a single coherent framework. By the late 20th century, physics had achieved something extraordinary. It had 2 theories, general relativity and quantum mechanics, that were each, in their own domains, the most precisely verified scientific theories in human history. General relativity predicts the behavior of massive objects with precision so extraordinary that GPS systems must account for relativistic time dilation to give you accurate navigation. Quantum mechanics predicts the properties of particles with accuracy so staggering that it has been called the most successful scientific theory ever devised. Together they seem to cover everything, the very large and the very small, the cosmic and the subatomic, and yet they cannot both be right, not in the way they are currently formulated, because when you try to combine them, the math falls apart. This is the wound at the center of modern physics. Not a new wound, but one that has been present for nearly a century, carefully managed, carefully avoided, carefully compartmentalized, so that science could continue doing what science does, making predictions, running experiments, building technologies. General relativity works beautifully for the large, quantum mechanics works beautifully for the small, but the universe is both. And when you apply both theories simultaneously, when you try to describe what happens in a black hole, where matter is compressed to quantum scales under gravitational conditions so extreme that relativity reaches its limits, the equations produce nonsense. Infinities appear where there should be finite values. The 2 most successful theories in the history of science become mutually incompatible, and that incompatibility is not a minor technical issue waiting for a fix. It is a signal that something in our understanding of reality is fundamentally incomplete, not just practically incomplete, structurally, philosophically, mathematically incomplete. String theory was supposed to be the answer. For decades, it attracted some of the most brilliant minds in physics with the promise of a unified framework, a theory in which the fundamental constituents of reality were not point-like particles, but tiny vibrating strings of energy, whose different vibrational modes produced what we perceive as different particles. In string theory, gravity and quantum mechanics could coexist. The infinities could be tamed. The gap between the very large and the very small could be bridged. It was mathematically seductive in a way that few theories in the history of science have been. It produced extraordinary results, discoveries in pure mathematics that had nothing to do with physics, but were beautiful in their own right. It suggested the existence of extra dimensions beyond the 4 we perceive, additional spatial dimensions curled up at scales far too small for any current instrument to detect. It offered a vision of the multiverse, an infinite space of possible universes, each with its own physical laws, each as real as our own. But after 50 years of development, string theory has produced no testable predictions that have been confirmed by experiment. Not one. It remains, for all its mathematical beauty, a framework that describes no experiment and explains no anomaly. It is a cathedral of pure thought, magnificent and empty of physical evidence. Loop quantum gravity, the other major candidate for a theory of quantum gravity, faces its own profound challenges: causal dynamical triangulations, asymptotic safety, non-commutative geometry. Each of these approaches represents a serious attempt by serious physicists to reconcile the incompatible frameworks, and each of them remains speculative, unverified, and disconnected from the experimental anomalies that are accumulating in labs and observatories around the world. The theoretical landscape of modern physics is littered with brilliant, internally consistent, mutually incompatible frameworks, none of which fully accounts for what we are actually observing. And meanwhile, what we are observing keeps getting stranger. Consider the muon. You might not spend much time thinking about muons. Most people do not. But the muon is currently at the center of one of the most intriguing and troubling experimental results in recent physics. A muon is a particle like an electron, but heavier, about 200 times heavier, and unstable, decaying into other particles after a fraction of a second. It is produced naturally by cosmic rays striking the upper atmosphere, and it is produced in accelerators, which is where it became the subject of a decades-long experiment at Brookhaven National Laboratory and later at Fermilab. The experiment is called the muon G-2 experiment, and its goal is to measure something called the magnetic moment of the muon with extraordinary precision. The magnetic moment is a property that describes how a particle responds to a magnetic field, how it wobbles, in a sense, when placed in a magnetic environment. The standard model predicts this value with extraordinary precision, and the measured value disagrees, not by a lot, not in a way that makes headlines outside of physics journals, but by an amount that statistically cannot be explained by random chance or measurement error. The discrepancy is small but real, and it suggests that something, some force, some particle, some interaction that the standard model does not include, is tugging on the muon in ways that the most complete theory of particles and forces ever devised fails to account for. Now, a discrepancy in the magnetic moment of a particle you have barely heard of might not feel like a reason for existential unease, but try to hold the full picture in your mind for a moment. The standard model is not just a good theory. It is the most precisely tested theory in the history of science. It predicted the existence of the Higgs boson, a particle that was confirmed by the Large Hadron Collider in 2012 after a 48-year search. It predicted the properties of particles before they were discovered. It has been refined over decades by thousands of physicists working with the most sophisticated instruments ever built. And it is wrong. Not completely wrong. It still works in the sense that most of its predictions are confirmed by experiment, but it is wrong in ways that matter. The muon anomaly tells us that there are interactions, forces, or particles that the standard model does not account for. The Hubble tension tells us that the cosmological framework built on top of the standard model is missing something fundamental about the expansion of the universe, and both of these anomalies point in the same direction, toward a reality that is larger, stranger, and more complex than our best theories currently describe. But even these anomalies, as significant as they are, do not fully capture how deep the strangeness goes. To feel the true vertigo of modern physics, you have to go to the places where the strangeness is not an anomaly, but the rule. You have to go to the quantum scale, because the world that quantum mechanics describes is not a world that human intuition, built by millions of years of evolution to navigate the medium-sized, medium-speed, medium-temperature world of everyday experience, can comfortably accommodate. It is a world where particles exist in multiple states simultaneously until they are observed. A world where two particles, separated by any distance, across a room, across a galaxy, across the observable universe, can be instantaneously correlated in ways that seem to violate everything we know about the speed of light and the limits of information transfer. A world where the act of measurement, of observation, of interaction, does not simply reveal a pre-existing reality, but participates in creating it. And the strangest part is not that this is speculative. The strangest part is that it has been verified, repeatedly, definitively, with extraordinary precision. The phenomenon is called quantum entanglement. When two particles interact under the right conditions, they become entangled, linked in a way that transcends ordinary spatial separation. Measure the quantum state of one particle, and you instantly know something about the state of the other, no matter where it is. Einstein hated this. He called it spooky action at a distance, and spent years arguing that it must be wrong. He believed that the apparent instantaneous correlation must be explained by what physicists call hidden variables, pre-existing properties of the particles that determine their measurement outcomes, and that quantum mechanics simply had not discovered yet. In other words, he believed the particles were like a pair of gloves separated and shipped to opposite ends of the world. If you open one box and find a left glove, you instantly know the other box contains a right glove. No spookiness required. The information was there all along. You just did not know it. The Bell inequality, formulated by physicist John Bell in 1964, provided a mathematical test that could distinguish between hidden variables and genuine quantum weirdness. And the experiments, culminating in Alain Aspect's landmark tests in 1982 and refined many times since, gave a definitive answer. Einstein was wrong. The correlations in entangled particles are not explained by hidden variables. There is no pair of eye gloves. The universe is, in some deep and irreducible sense, non-local. What happens at one point in space can be correlated with what happens at another point in space in ways that cannot be explained by any influence traveling between them, not even at the speed of light. What does that mean? Physicists will tell you carefully that it does not mean information is traveling faster than light. You cannot use entanglement to send a message, to communicate instantaneously across space, because the correlations only become apparent when you compare notes through an ordinary, light-speed limited channel. The universe, it seems, has arranged itself so that non-locality exists at the quantum level, but cannot be exploited for faster-than-light communication. That is reassuring, in a technical sense. But think about what it actually means. The universe contains correlations, real, measurable, physically verified correlations that are not explained by any local physical process. There is no signal passing between the particles. There is no hidden mechanism. There is just correlation, instantaneous and irreducible, built into the fabric of reality at its most fundamental level. The universe is connected in ways that nothing in our everyday experience prepares us to understand. And the framework that describes this connection, quantum mechanics, is the most successful scientific theory ever constructed. We built our most successful science on a foundation we do not understand. That sentence deserves to sit in your mind for a moment, because it is not hyperbole. Physicists use quantum mechanics every day to design computer chips, to develop medical imaging technologies, to calculate the properties of materials. The predictions work, the applications work, the technology works, and yet the interpretation, what quantum mechanics actually means about the nature of reality, remains one of the deepest, most contested, most unresolved questions in all of science. Is the wave function a description of reality, or just a tool for calculating probabilities? When a quantum event occurs and a definite outcome is produced, what exactly happens? What determines which outcome occurs? Who or what constitutes an observer? Does consciousness play a role? Does the universe branch into parallel versions at each quantum event, as the many worlds interpretation suggests? Or is reality fundamentally probabilistic, with nothing predetermined until the moment of observation, as the Copenhagen interpretation suggests? These are not fringe questions. They are the central interpretive questions of the most fundamental theory of physics, and a century after that theory was developed, they remain without consensus. The fact that you can use a theory without understanding it is, in one sense, a testament to the power of mathematics, the ability to compress reality into equations that predict without necessarily explaining. But it is also, in another sense, a warning, because the history of science is full of cases where a theory worked in its domain until it did not, until it hit a boundary case, a new experiment, a measurement that pushed it beyond the regime where its predictions held. And when that happened, the theory did not just fail to predict the new phenomenon. It revealed that what the theory had described all along was not the thing itself, but a very good approximation of the thing. An approximation so good that it produced accurate results in most situations, but one that was, at the deepest level, incomplete. Newton's laws are still used by engineers and navigators. They work, but they are not the final truth. They are an approximation of general relativity, valid for objects moving slowly compared to the speed of light, and general relativity itself is likely an approximation of something deeper, something that resolves its conflict with quantum mechanics, something that explains the Hubble tension, something that accounts for the anomalous magnetic moment of the muon. We just do not know what that something is yet, or perhaps the word yet is optimistic in a way that is itself worth questioning. There is a strand of thought in modern physics, not mainstream but not fringe either, that suggests the problem is not just that we have not found the right theory. The problem might be that the kind of theory we are looking for, a mathematical framework that completely and consistently describes all of physical reality, might not exist. Or it might exist but be beyond the cognitive reach of a primate brain that evolved for an entirely different purpose. The physicist Niels Bohr once said that anyone who is not shocked by quantum mechanics has not understood it. But perhaps the deeper insight is not just that quantum mechanics is shocking, but that the shock never resolves. That the strangeness is not a temporary feature of an incomplete theory, but a permanent feature of a reality that is irreducibly strange. That the universe is not just complicated, It is, at its foundation, different in kind from anything that human intuition can contain, and this is where the journey from physics becomes something else, something harder to name. Because when you follow the anomalies far enough, the Hubble tension, the muon anomaly, the measurement problem, the incompatibility of quantum mechanics and general relativity, you eventually arrive at a question that is not just about equations or particles or the rate of cosmic expansion. You arrive at a question about the relationship between mind and reality, about what it means to observe, to know, to exist in a universe that may not be fully knowable, about whether the tools we use to understand the universe, our instruments, our mathematics, our models, our very minds, are adequate to the task of understanding what the universe actually is. The physicist John Wheeler, who coined the term black hole and spent decades at the frontier of quantum mechanics and general relativity, believed that observation was not just a passive act of registration, but an active participant in the construction of reality. He proposed what he called the participatory anthropic principle, the idea that the universe at the quantum level does not fully exist without observers to collapse its possibilities into actualities. He imagined, and partly calculated, that even light from the distant past, light that left its source billions of years ago, does not have a definite path until it is observed, that the act of observation now reaches back into the past and selects which trajectory the light took. This is not science fiction. It is a serious theoretical proposition, grounded in quantum mechanics, consistent with the mathematics. And if it is correct, if observation genuinely participates in the construction of physical reality, then the observer is not separate from the universe being observed. The observer is part of the experiment, and that means that the universe you are living in, the universe you are perceiving, is not a fixed and independent object that you are passively looking at. It is something that your act of looking is, in some sense, helping to create. You can feel the vertigo of that idea if you let yourself. The ordinary experience of being a human in the world is predicated on a very specific assumption that things exist independently of whether you are looking at them, that the chair you are sitting on does not pop in and out of existence based on your awareness of it, that the sun rises whether or not there is anyone to see it, that reality is independent, solid, and pre-existing. This assumption is so fundamental to normal human experience that it does not feel like an assumption at all. It feels like the bare minimum of what it means for anything to be real. And quantum mechanics, not as a philosophical interpretation, but as a direct consequence of its experimental results, puts pressure on exactly this assumption. Not enough to make chairs uncertain. The quantum effects that make particles behave as waves of probability, that generate the correlations of entanglement, that produce the measurement problem. These effects wash out at the scales of everyday objects through a process called decoherence. The chair is not in quantum superposition in any meaningful way, but the fact that the classical world you inhabit is built out of a quantum substrate that at its foundation, reality, is governed by laws that violate the intuitions of classical solidity, is not nothing. It is something. Something that keeps some of the deepest thinkers in physics awake at night. And here is where dark matter enters the picture, not as a metaphor, but as an actual scientific concept, one of the most important and least understood in all of modern physics. The name is evocative but misleading. Dark matter is not dark in the way that darkness is the absence of light, though it does not emit, absorb, or reflect electromagnetic radiation. It is dark in the sense of invisible, undetectable by any direct method we currently possess. We know it exists, if it exists, not because we have seen it, but because of what we see and what does not add up. The rotation curves of galaxies are the most direct evidence. Stars and galaxies orbit the galactic center the way planets orbit the sun, under the influence of gravity, and the way things orbit under gravity follows predictable rules. Stars, farther from the center of a galaxy, should orbit more slowly than stars closer in, just as the outer planets of the solar system orbit the sun more slowly than the inner planets. This is what Newton and Kepler would predict. This is what the visible mass of the galaxy would produce. But that is not what we observe. Stars in the outer regions of galaxies orbit at the same speed, sometimes even faster, than stars closer to the center. The rotation curves are flat where they should slope, downward. This discrepancy is enormous, and it is seen across virtually every galaxy we can measure. The only explanation that fits within the framework of general relativity is that galaxies are embedded in vast halos of invisible matter. Matter that has mass, that exerts gravitational force, but that does not interact with light or with ordinary matter in any way that we can detect. Dark matter. And the calculations suggest that there is more of it than there is ordinary matter. Not just slightly more, but approximately 5 times more. The universe you can see, the stars and planets and galaxies and nebulae, represents roughly 5% of the total mass energy content of the universe. The remaining 95% is something we cannot see, cannot detect directly, and cannot explain. But dark matter, strange as it is not the strangest part. The strangest part is dark energy. In 1998, 2 independent teams of astronomers studying Type Ia supernovae at extraordinary distances made a discovery so unexpected that it initially seemed like a measurement error. They were trying to measure the rate at which the expansion of the universe was slowing down. Because it seemed obvious, it still seems obvious intuitively, that a universe that began with an explosion would be gradually decelerating as gravity, acting across cosmic scales, pulled everything back toward everything else. Like a ball thrown into the air, the universe should be expanding more slowly over time. Both teams were measuring by how much, and both teams found the opposite. The expansion was not decelerating, it was accelerating. The universe was expanding faster and faster, driven by some invisible, pervasive energy, dark energy, that was not only overcoming gravity on the largest scales, but actually winning. The acceleration was increasing. The universe was not coasting to a halt or collapsing back on itself. It was running away. The discovery earned the team leaders, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011. It was celebrated as one of the great discoveries of modern cosmology, and it was also, in a very real sense, one of the most disturbing things that science has ever found, because dark energy, this dominant constituent of the universe, this force that governs the ultimate fate of all existence, is almost completely unexplained. The only theoretical concept that resembles it is Einstein's cosmological constant, the same term he added to his equations to produce a static universe, the same term he later called his greatest blunder. Restored as a description of dark energy, the cosmological constant works mathematically. It matches the observations, but what it represents physically, what is actually producing this energy that fills all of space and drives the acceleration, is unknown. The most natural interpretation from quantum field theory is that it represents the energy of empty space itself, the zero-point energy that quantum mechanics predicts should fill the vacuum. But when physicists calculate what that zero-point energy should be, they get a value that is somewhere between 10 to the 60th and 10 to the 120th times larger than the observed value of the cosmological constant. That discrepancy between what the most fundamental theory of matter predicts and what we actually observe is the largest known discrepancy between theory and observation in all of science. It has been called the worst prediction in the history of physics, and it has no satisfying explanation. Take a moment with that. The largest discrepancy between theory and observation in the entire history of science, in the most fundamental area of physics, describing the dominant constituent of the entire universe. Not a small problem, not a detail. The central fact of cosmology, that the universe is filled with an accelerating energy, is described by a mathematical parameter that either means nothing or means something we cannot calculate, or requires a resolution that lies beyond the current boundaries of physical theory. And all around this central void of understanding, the anomalies cluster, the Hubble tension, the muon anomaly, the incompatibility of quantum mechanics and general relativity, the absence of direct detection of dark matter despite decades of experiments designed with increasing sophistication to find it. Each of these is a separate problem. Each has its own technical literature, its own community of expert researchers, its own proposed solutions. And yet, they share something. They share the quality of being cracks in the same foundation, different expressions of the same underlying incompleteness. The direct detection of dark matter is worth dwelling on for a moment. If dark matter is real, if it makes up 27% of the mass energy content of the universe, then it should be everywhere. Right now, as you are reading this, dark matter particles, whatever they are, should be streaming through your body, through the Earth, through the entire planet, at millions per second. You feel nothing. You are unaware of it. But based on the calculations, if dark matter is made of the kind of particles that most theorists have predicted, weakly interacting massive particles, or WIMPs, those particles should occasionally interact with ordinary matter in ways that are, detectable with sensitive enough instruments. And physicists have built those instruments. Detectors buried deep underground to shield them from cosmic radiation. Detectors filled with noble gases cooled to near absolute zero. Detectors of increasing sensitivity, running for years, scanning for the faint signature of a WIMP scattering off an atomic nucleus. And they have found nothing, no signal. In some experiments, tantalizing hints have appeared and then faded, but no confirmed, reproducible, statistically definitive detection of a dark matter particle. The most motivated, theoretically well-supported candidate for dark matter has so far simply not been found, which leaves open the possibility that dark matter is not WIMPs, that it is something else, that it is something we have not thought of yet, or that the observations that led us to infer dark matter's existence are being misread, that what we interpret as evidence for invisible matter is actually evidence of something else entirely, a modification of gravity at large scales, a new force, something that requires the entire framework of general relativity to be reconsidered. Modified Newtonian dynamics, MOND, is one such proposal. Developed by physicist Mordechai Milgram in 1983, MOND suggests that Newton's law of gravity is modified at very low accelerations, the kind of accelerations experienced by stars in the outer regions of galaxies. In the MOND framework, gravity does not fall off in the standard way at large distances. It falls off more slowly, producing the flat rotation curves we observe without requiring any invisible matter. MOND was initially regarded as a curiosity, perhaps a useful empirical relation, but not a fundamental theory. And it has significant problems. It does not easily account for the behavior of galaxy clusters, and it has difficulty fitting into the relativistic framework required for cosmology. But it is worth knowing that it exists, because MOND, for all its limitations, does something that the dark matter hypothesis has so far failed to do. It makes specific, testable, successful predictions about the internal dynamics of individual galaxies. The radial acceleration relation, the observed tight correlation between the gravitational acceleration in galaxies and the distribution of visible matter, falls naturally out of MOND. It requires fine-tuning in dark matter models. This does not mean MOND is right, but it means that the question of what produces the gravitational anomalies we observe in galaxies is genuinely open and genuinely important. The possibility that gravity itself is not what we think it is has implications that are almost too large to hold. Gravity is the most intuitive force. It is the force you feel in your body, the force that keeps you connected to the Earth, the force that shaped the planet you live on, the solar system you live in, the galaxy you live inside. It is the force that Einstein showed is not really a force at all, but the curvature of space-time caused by mass, a geometric property of the universe itself. To modify gravity is to modify space-time. To modify space-time is to modify the foundation on which everything else in physics rests. And yet, the evidence suggests that either the universe is filled with 5 times more matter than we can see, or gravity does not behave the way we think it does, or both of these things are, in some deeper theoretical framework, connected. We are not sure which. We are not sure how to find out. And in the meantime, the universe keeps expanding, the anomalies keep accumulating, and the theories keep proliferating without converging. You might ask, why does this not bother people more? Why is not the failure to explain 95% of the universe, the failure to reconcile the 2 most successful theories in physics, the failure to detect dark matter after decades of searching, the discrepancy in the Hubble constant, why is not this treated as the crisis that, by any reasonable assessment, it is? The answer is partly sociological and partly psychological, and it tells you something important about how humans relate to knowledge. Partly the reason is that physics keeps working. Bridges stand. GPS satellites navigate accurately. MRI machines produce detailed images of living tissue. Nuclear reactors generate power. The technology built on the foundations of modern physics continues to function. To improve, to transform the world in ways that feel like confirmation of everything the underlying science claims to know. And when the technology works, it is very hard to feel the crisis in the theory. The crisis lives in the equations, in the papers, in the conference presentations where physicists speak to other physicists in a language of mathematical abstraction that most people will never encounter. It does not leak into the everyday world in ways that are easy to feel, but the crisis is real, and it is worth feeling, even if feeling it requires a deliberate effort of imagination. Because what is at stake is not just the accuracy of a set of equations. What is at stake is the question of whether the project of physics, the project of understanding reality through observation, mathematics, and reasoning, is converging toward truth, or whether it is approaching a limit not of effort or intelligence or technology, but of the kind of understanding that is possible for beings like us in a universe like this. That question, the question of limits, is not new to philosophy. It is, in many ways, the central question of epistemology, the branch of philosophy concerned with the nature and boundaries of knowledge. What can we know? How do we know it? And crucially, are there things that, by their nature, cannot be known? Immanuel Kant, writing in the 18th century, drew a famous distinction between phenomena, the world as it appears to us, structured by the categories of our perception and understanding, and noumena, the world as it is in itself, independent of any observer. Kant argued that we can never have direct access to the noumenal world. Our knowledge is always mediated by the structure of our minds, by the forms of intuition, space and time, and the categories of understanding that we bring to every experience. We do not perceive reality directly. We perceive reality filtered through the architecture of human cognition. And that architecture, however powerful, however refined by evolution and culture, is finite. It was built for survival, not for cosmic truth. The fact that it has taken us as far as it has, to quantum field theory, to general relativity, to the detection of gravitational waves from colliding black holes a billion light-years away, is extraordinary. But extraordinary is not the same as unlimited. The physicist and philosopher David Deutsch has argued the opposite view with great force and eloquence. In his framework, there are no in-principle limits to human knowledge. Problems that are not understood yet are simply unsolved, and all unsolved problems are in principle solvable. Knowledge grows without bound, not because human minds are infinite, but because the process of conjecture and refutation, the Popperian scientific method, refined and extended, is capable of producing ever better explanations that get closer and closer to the truth. In Deutsch's view, the anomalies in physics are not evidence of limits. They are evidence of the next revolution, the next conceptual shift that will, in retrospect, seem as natural and inevitable as Einstein's extension of Newton, or Newton's extension of Kepler. The crisis in physics is not a crisis of knowledge. It is a crisis of current knowledge, and there is a profound difference. Both positions are coherent, both are held by serious thinkers, and the tension between them is not merely academic. It shapes how you approach the unknown. If Deutsch is right, then the Hubble tension, the muon anomaly, the incompatibility of quantum mechanics and general relativity, these are solvable problems, and the solution will come from human minds doing what human minds have always done at the frontier of knowledge: guessing, testing, revising, and guessing again. If something closer to the Kantian view is right, if the structure of human cognition places genuine limits on the kind of understanding we can achieve, then we may be entering a territory where the universe is giving us data that we cannot interpret, where the measurements are real, but the framework for understanding what they mean is beyond our reach, where the crisis in physics is not a crisis of current knowledge, but a permanent feature of the relationship between finite minds and an infinite reality. And perhaps the most honest position is that we do not know which of these is true. We are in the middle of the story. We cannot see the ending, and there is something profound in that, something that calls for a quality of mind that is rare and difficult to cultivate, the ability to sit with genuine uncertainty, not the fake uncertainty of political debate, where positions are preformed and uncertainty is performed, not the comfortable uncertainty of problems that are hard but clearly solvable, but the deep, structural, possibly permanent uncertainty of standing at the edge of what is knowable and looking into something that may or may not yield to any framework you are capable of constructing. This is where philosophy becomes not just relevant, but essential. Not philosophy as abstract wordplay, but philosophy as the discipline of thinking carefully about things that resist easy resolution. The relationship between mind and reality, the nature of explanation, the difference between a theory that works and a theory that is true, the meaning of scientific progress when the frontier stops advancing and starts revealing complexity that grows faster than understanding. These are not decorative questions to be addressed after the real science is done. They are foundational questions that determine whether the real science can even be properly understood. And the most important of them, for our purposes, is one that goes back at least to Plato and has not been conclusively answered since. What is the relationship between the mathematical structures that describe reality and reality itself? The unreasonable effectiveness of mathematics is a phrase coined by physicist Eugene Wigner in a famous paper written in 1960. Wigner was struck by something that, once you notice it, is genuinely astonishing. The mathematics developed by pure mathematicians, often for entirely abstract reasons, with no application in mind, purely as an exploration of logical structure, turns out, repeatedly and unexpectedly, to describe physical reality with extraordinary precision. Non-Euclidean geometry, developed by mathematicians in the 19th century as an abstract exploration of what geometry would look like if you removed one of Euclid's axioms, turned out to be exactly the mathematics Einstein needed to formulate general relativity. Group theory, a branch of abstract algebra, turned out to be exactly the mathematical framework that described the symmetries of particle physics. Complex numbers, imaginary quantities invented to solve equations that had no real number solutions, turned out to be fundamental to quantum mechanics, not as a convenient tool, but as part of the deep structure of physical reality. Why? Why should the abstract creations of the human mathematical imagination correspond so precisely to the structure of a universe that existed for 13.8 billion years before mathematicians began exploring it? There are a few possible answers, and each of them is philosophically radical. The first is mathematical Platonism, the view that mathematical structures are not invented, but discovered, that they exist independently of human minds, in some abstract realm of pure logical necessity, and that physical reality is instantiated within or governed by these structures. On this view, the unreasonable effectiveness of mathematics is not unreasonable at all. It is to be expected. Mathematics describes reality so well because reality is mathematical. Not that reality behaves according to mathematical rules, but that reality is, at its deepest level, a mathematical structure. The physicist Max Tegmark has developed this view into a full cosmological hypothesis called the mathematical universe hypothesis. The proposal that our physical universe is not just described by mathematics, but is itself a mathematical structure. Every universe that is mathematically consistent exists physically. The multiverse is the totality of all mathematical structures, and we live in one of them. This is a view that is both breathtaking in its ambition and deeply unsatisfying to many scientists and philosophers for reasons that are not merely aesthetic. If every mathematical structure exists physically, the hypothesis is untestable by definition. You cannot step outside the mathematical structure you inhabit to confirm or deny the existence of others. It is a beautiful idea that may be permanently beyond the reach of empirical verification, which, to a Popperian, makes it not science but metaphysics, however mathematically respectable. A second possible answer is more deflationary. Mathematics works because humans developed mathematics by abstracting patterns from physical reality. We invented geometry by studying the shapes of things. We invented arithmetic by counting objects. The deep connection between mathematics and physical reality is not mysterious. It is a consequence of the fact that mathematics is built, at its roots, from observations of the world. On this view, it is not surprising that mathematics describes the world. Mathematics is a refined, abstracted, formalized version of the world. This view is reassuring, but it struggles to explain why mathematics developed in entirely abstract directions, away from any physical motivation, so consistently turns out to describe physics discovered centuries later. The connection is too frequent, too precise, too nonlinear to be fully explained by the historical origins of mathematics. A third possibility is the most unsettling of all. Perhaps the connection between mathematics and reality is not explaining something true about the universe, but revealing something about the limits of human understanding. Perhaps the only things we can fully comprehend about reality are the things that fit into mathematical structures, because mathematical structure is the form that human rational thought takes. Perhaps reality contains far more than its mathematical aspects, and we only perceive the mathematical parts because those are the parts our minds can process. On this view, physics does not describe reality. It describes the mathematical shadow of reality, the part that is legible to mathematical minds. And the rest, whatever the rest might be, is permanently beyond our reach, not because it is hidden, but because the tools we have for understanding were not built to see it. This idea connects to something important in the philosophy of science that is often overlooked in the excitement of discovery, the concept of underdetermination. In philosophy of science, underdetermination refers to the fact that for any finite set of observations, there are in principle infinitely many theories consistent with those observations. The data does not determine the theory. The observations do not select a unique explanation. Every time physics produces a framework that matches the data, there are other frameworks, perhaps infinitely many, that would match the same data equally well, making different predictions only in domains not yet explored. This does not mean that all theories are equally good. Some are simpler, some are more powerful, some make more additional predictions that get confirmed, but it means that the process of converging toward the truth is never guaranteed. It means that the history of science, which looks from the outside like a steady march toward better and better descriptions of reality, is also a history of frameworks that worked until they did not, that seemed complete until the next generation of instruments or experiments found the crack. And, right now, the cracks are visible, more visible than they have been in decades. The Hubble tension represents a crack in the standard model of cosmology. The muon anomaly represents a crack in the standard model of particle physics. The incompatibility of quantum mechanics and general relativity represents a crack in the entire foundation of physics. The failure to explain the cosmological constant represents a crack in the connection between particle physics and cosmology. Each crack is real. Each has been verified and re-verified. Each is being studied by brilliant people with every tool that science can bring to bear, and none of them has been resolved. It would be wrong to say that this represents a crisis in the popular sense, a disaster, a failure, a collapse. Science is not failing. It is working exactly as it should. It is doing what it has always done, following the evidence wherever it leads, even when where it leads is uncomfortable, even when where it leads is into territory that the existing framework cannot contain. The history of science is the history of frameworks that were extended, revised, or overthrown when the evidence demanded it. Newton's mechanics was not a failure. It was a profound achievement that described reality accurately within its domain, and that was eventually embedded into the larger framework of relativity when new evidence demanded a larger framework. The same will likely be true of the standard models of cosmology and particle physics. They will be extended, revised, embedded into something larger and stranger, and the anomalies that seem so troubling today will become, in retrospect, the clues that pointed the way. But that retrospective view, the view from the future looking back at the obvious path, is not available to us now. We are in the present. We are inside the crisis. And inside the crisis, the feeling is not one of steady progress, but of genuine disorientation, of standing at a boundary and not knowing whether you are at the edge of the next discovery or the edge of the discoverable. That feeling has a name in philosophy. It is called the aporia, a term from ancient Greek that means, literally, the pathless path, the place where the road runs out. The moment in an argument when every direction seems blocked, where every proposed solution creates new problems, where the usual ways of thinking simply stop working. Plato used it to describe the moments in the Socratic dialogues when all the proposed definitions of virtue or justice or knowledge had been refuted, and the participants were left not with an answer, but with a clarified appreciation of how hard the question was. The aporia is not failure. It is, in the Socratic tradition, the beginning of real thinking, the moment when you realize that what you thought you knew was only what you thought, and that genuine knowledge, if it is possible, requires going somewhere you have not been. The aporia of modern physics is something like this. We have four fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. We have a mathematical framework, quantum field theory, that successfully describes three of them. We have a separate mathematical framework, general relativity, that describes the fourth. We cannot combine them. We have particles, the quarks, leptons, and bosons of the Standard Model, whose properties we can measure with extraordinary precision. And we have anomalies in those measurements that the Standard Model cannot explain. We have a universe whose expansion we can measure two different ways, and the two measurements disagree. We have evidence for a dominant constituent of the universe, dark energy, whose nature we do not understand. We have evidence for another dominant constituent, dark matter, that we have not directly detected. We have a theory, quantum mechanics, that is the most successful in the history of science and whose interpretation remains genuinely controversial after a century of effort. Every one of these is a pathless path. Every one of them represents a place where the road runs out, where the usual methods of physics are being applied with full force and producing either nothing or results that deepen the mystery. The philosopher of science Thomas Kuhn, in his landmark work, The Structure of Scientific Revolutions, described the history of science not as a linear accumulation of knowledge, but as a series of what he called paradigms, frameworks for understanding the world that define what counts as a valid problem, what counts as a valid solution, and what counts as evidence. Within a paradigm, science makes progress. Puzzles are solved. The framework is refined and extended. Anomalies appear, but they are treated as puzzles to be solved within the existing framework, not as signs that the framework itself is wrong, until they are not, until the anomalies accumulate to the point where they can no longer be accommodated within the framework, until scientists begin to recognize that the anomalies are not puzzles within the paradigm, but symptoms of its limitations. And then, sometimes suddenly, sometimes over decades, the paradigm shifts. A new framework emerges that can accommodate what the old one could not. What was anomaly becomes explanation. What was crisis becomes revolution. Kuhn did not claim that paradigm shifts always bring us closer to the truth. He was actually quite careful about that. He argued that successive paradigms are not simply more accurate versions of their predecessors, but genuinely different ways of seeing the world, different in ways that make them incommensurable, not fully translatable into each other. Newtonian mechanics is not just a less accurate version of general relativity. It is a framework built on different concepts: absolute space, absolute time, forces acting at a distance that do not survive the transition to relativistic mechanics. The transition involved not just new equations, but new concepts, new ontologies, new ways of thinking about what space and time are. And the transition to whatever comes after the current frameworks in physics will likely involve the same kind of conceptual discontinuity. Not just new equations, but new ways of thinking about what matter is, what space is, what time is, what observation means, what reality means. That is both exciting and terrifying. Exciting because revolutions in understanding are the moments when human knowledge makes its most dramatic leaps. Terrifying because they involve the dissolution of things that felt like certainties, frameworks that were not just intellectually compelling, but deeply embedded in the way educated people understood the world. When the Copernican revolution removed the Earth from the center of the universe, it was not just an astronomical adjustment, it was an ontological earthquake. When Darwin's theory of natural selection removed the design argument from biology, it was not just a change in scientific theory, it was a transformation in the way humans understood their own place and purpose. When quantum mechanics demonstrated that nature at its foundation is not deterministic, that there are events with no sufficient prior cause, or no definite state until observed, it was not just a new set of equations, it was a philosophical rupture, the consequences of which we are still working through. The next revolution will be no different, and we are perhaps already in its early stages. The signs of a paradigm in crisis, in Kuhn's sense, are not hard to find in current physics. The proliferation of proposals that cannot be tested experimentally, the growing gap between theoretical development and observational confirmation, the sense among working physicists, expressed increasingly openly in papers, conferences, and popular writing, that the current approaches are not working, that something fundamental is missing, that the enormous technical sophistication of modern theoretical physics has produced diminishing returns on actual understanding. The Large Hadron Collider, the most powerful particle accelerator ever built, discovered the Higgs boson in 2012, a triumph, but has found no convincing evidence for any of the proposed extensions of the Standard Model that theorists had been developing for decades. Supersymmetry, which was supposed to appear at the energy scales the LHC can access, has not appeared. Extra dimensions predicted by string theory have left no trace. The particles that were supposed to be there, according to the best motivated theoretical extensions of the Standard Model, are not there. Or if they are there, they are hiding in regions of parameter space that are becoming increasingly contrived and implausible. This is not crisis in the popular sense, but it is pressure. It is the pressure of a framework being tested and not confirming its predictions over and over, with increasing precision and increasing silence. And perhaps the most philosophically significant aspect of this moment is what it forces on us regarding the relationship between beauty and truth. One of the deepest, most influential, and most controversial ideas in theoretical physics is that beautiful mathematics is a guide to physical truth, that elegant equations are likely to be right, that theoretical simplicity and mathematical grace are signs of contact with something deep and true about the structure of reality. This idea has a distinguished history. Einstein's field equations of general relativity are widely regarded as among the most beautiful mathematical expressions in physics. Dirac's equation, which described the electron relativistically and predicted the existence of antimatter, was valued by its author partly for its mathematical beauty. The Higgs mechanism, the gauge symmetry of the Standard Model, these have the quality of mathematical elegance that physicists use as a compass when experiments are not yet available to guide them. String theory, which began as an attempt to describe the strong force and evolved into a candidate theory of everything, has attracted and retained some of the most gifted theoretical physicists alive, partly on the basis of its mathematical beauty and richness. Its advocates argue that something so mathematically profound must have a connection to physical reality, even if that connection has not yet been demonstrated. But what if they are wrong? What if beauty is not a guide to truth, but a guide to what human minds find aesthetically satisfying, which may or may not overlap with the structure of an indifferent universe? The history of science contains as many beautiful theories that turned out to be wrong as it does beautiful theories that turned out to be right. Kepler believed the planets orbited in paths corresponding to the nested Platonic solids, a model of breathtaking mathematical elegance that was simply incorrect. The steady-state model of the universe, which proposed that new matter was continuously being created to maintain a constant average density as the universe expanded, was mathematically elegant and deeply satisfying to its proponents, and was overturned by the discovery of the cosmic microwave background. Elegance is a property of theories in relation to the minds that evaluate them. It tells us something about the structure of human aesthetic experience. It may or may not tell us something about the structure of reality. This tension between the apparent deep connection between mathematics and reality, and the possibility that this connection is partly a projection of human cognitive tendencies onto an indifferent universe, is one of the defining philosophical tensions of contemporary science. And it is not a tension that can be resolved by more data. It is a philosophical question, a question about the nature of knowledge, the nature of explanation, and the nature of reality itself. And answering it, or even approaching it with the seriousness it deserves, requires the kind of thinking that physics alone cannot provide. It requires philosophy. It requires the patient, careful, rigorous analysis of foundational concepts that philosophical inquiry, at its best, can offer. This is not a sentimental defense of philosophy as a soft complement to hard science. It is a claim about necessity, at the frontier of physics, where the frameworks are cracking, where the anomalies are multiplying, where the very concepts that have organized scientific thinking for a century are under pressure. The questions that arise are not empirical questions in the usual sense. They are questions about the conceptual foundations of inquiry itself. What is it for a theory to explain something, rather than merely describe it? What is the relationship between a model and the reality it represents? What does it mean for something to be real in a context where reality at its fundamental level behaves in ways that defy classical intuition? These are philosophical questions, and they need philosophical answers, not to replace the physics, but to think clearly about what the physics is telling us. The philosopher Willard Van Orman Quine famously argued that there is no sharp boundary between science and philosophy. Both are engaged in the project of understanding the world, and both are subject to revision in light of new discoveries. Scientific theories have philosophical commitments built into them. Commitments about causation, about the nature of space and time, about what kinds of entities are real. Philosophical positions have empirical consequences. They shape what kinds of experiments seem relevant, what kinds of evidence seem compelling, what kinds of explanations seem satisfying. Quine called this the web of belief, the idea that our knowledge is not a set of independent propositions, each connected directly to experience, but an interconnected web in which changes anywhere can produce changes everywhere. When the anomalies in physics pull on one part of the web, when the Hubble tension, or the muon anomaly, or the measurement problem tugs at the foundations, the effects propagate through the entire web, through cosmology, through particle physics, through the philosophy of science, through our deepest assumptions about what knowledge is and what reality is. We are, in this moment, feeling the propagation. Not in the everyday world, where bridges stand and GPS satellites navigate and MRI machines image living tissue, but in the domain of foundational inquiry, in the domain where the questions are not about how things work, but about what things are, about why the universe is lawful, about whether the lawfulness is real or projected, about whether the universe had a beginning, and what, if anything, preceded it, about whether it will have an end, and what the end will be. These questions have always been part of what it means to be a reflective human being. They are not new, but they are newly urgent, because the tools we have built to answer them have brought us to the edge of what they can reach, and we are standing there, looking into whatever lies beyond, with instruments that may or may not be adequate, and minds that are certainly finite, asking questions that may or may not have answers we can find. There is a particular moment in the history of cosmology that captures this feeling with unusual clarity. In 1931, Georges Lemaitre, the Belgian priest and physicist who had proposed the idea that the universe began from what he called the primeval atom, was at a meeting where Einstein presented his latest work. Einstein expressed doubts about the expanding universe. Lemaitre pressed him. What did Einstein think the beginning of the universe would look like, in physical terms? Einstein reportedly did not have an answer. The mathematics of general relativity broke down at the beginning, what physicists call the initial singularity, the point where the equations produced infinite density and infinite temperature, and effectively stopped providing any information about what came before. Einstein knew that his theory was not adequate to describe the beginning. He said so, in one form or another, throughout his later life. The beginning was beyond the reach of the theory, not because the theory was bad, it was, and remains the best description of gravity and space-time ever devised, but because there are conditions in which any theory becomes inadequate. The beginning of the universe appears to be one of them. What came before the Big Bang? The question sounds simple. It is, in fact, one of the deepest questions in all of physics and philosophy, and the honest answer, the scientifically honest, philosophically honest answer, is that we do not know. We have conjectures, we have models. Some physicists argue that the question is meaningless because time itself began with the Big Bang, and asking what came before is like asking what is north of the North Pole, a question that assumes a framework that does not apply. Stephen Hawking and James Hartle developed a model, the no-boundary proposal, in which the universe has no initial boundary in time, in which the beginning of time is smooth and finite, in the same way that the surface of a sphere has no edge, despite being finite. In this model, there is no moment before the Big Bang, not because the question is unanswerable, but because the question contains a false premise. Time, in this model, does not extend backward infinitely, but neither does it begin at a sharp boundary. It fades gracefully into a quantum foam of geometry that requires no prior cause. This is a beautiful idea. It is also completely untestable with current technology, and it is one among several genuinely distinct competing models, each with its own proponents and its own problems. Others propose that the Big Bang was not a beginning but a transition, a bounce from a previous phase of cosmic evolution, a collapse followed by an expansion, a cycle that may have repeated indefinitely, or may have begun at some point for reasons that the cycle itself cannot explain. The cyclic cosmology of Paul Steinhardt and Neil Turok, the loop quantum cosmology of Abhay Ashtekar, the conformal cyclic cosmology of Roger Penrose, each of these offers a different vision of the universe's deep past and ultimate future. Each is mathematically developed, theoretically serious, held by physicists of genuine distinction, and each is, for now, beyond the reach of experimental confirmation. Roger Penrose, whose contributions to theoretical physics span 6 decades and include fundamental work on black holes, quantum mechanics, and cosmology, has in recent years become one of the most provocative voices in the conversation about consciousness and reality. His view, developed with anesthesiologist Stuart Hameroff, proposes that consciousness is not a product of classical computation in the brain, but arises from quantum processes, specifically from what Penrose and Hameroff call orchestrated objective reduction, a process in which quantum superpositions in the microtubules of neurons collapse in ways that are governed by objective features of space-time geometry. This proposal is controversial, deeply controversial, and most neuroscientists and quantum physicists regard it with skepticism. The quantum coherence required for such processes seems unlikely to be maintained in the warm, wet, noisy environment of a biological brain. But Penrose's motivation for the proposal is philosophically important, regardless of whether the specific mechanism is correct. He argues, rigorously from formal logic, that human mathematical understanding cannot be fully captured by any computational system, by any algorithm, by any set of rules that could be programmed into a Turing machine. His argument draws on Gödel's incompleteness theorems, the remarkable mathematical results that showed, in 1931, that any sufficiently powerful formal system contains truths that cannot be proven within the system. Penrose argues that human mathematicians, in their ability to perceive mathematical truths that transcend any formal system, must have access to something that is not computational, and that something, he believes, is a new kind of physics, a physics that does not yet exist, that requires the unification of quantum mechanics, general relativity, and the theory of consciousness. Whether Penrose is right about the specific conclusions is less important, for our purposes, than what the argument reveals about the position we are in. We are trying to understand the universe with tools that are products of the universe. Our brains, whatever consciousness is, are physical objects that evolved within physical reality, subject to its laws, limited by its structure. The instruments we build are extensions of those brains, projections of our cognitive architecture into material form. The mathematics we use to describe reality is a product of mathematical minds, refined over centuries by a species with a particular evolutionary history. And yet we are applying all of this, these thoroughly situated, thoroughly physical, thoroughly evolved tools, to questions about the totality of physical reality, including the questions of what physical reality is, whether it has a beginning, whether it has a cause, whether it is all there is. The circular quality of this enterprise is something that most working scientists do not dwell on, for good practical reasons. If you dwell on the epistemological foundations of every experiment you run, you will never run any experiments. Science requires a kind of methodological confidence, a willingness to treat the frameworks as provisionally correct and push forward, to treat the anomalies as problems to be solved rather than signs of permanent ignorance. That confidence is not naive. It is earned by the extraordinary track record of scientific progress, but it is also, at the deepest level, a bet that the universe is, in principle, comprehensible to beings like us, that the tools we have built, mathematical, experimental, conceptual, are adequate, at least in principle, to the task of understanding what the universe is, that the strangeness of quantum mechanics, the dark sectors of cosmology, the fundamental incompatibility at the heart of physics, that all of this is solvable, in some eventual sense, by some eventual refinement of the methods that have brought us this far. It is a bet worth making. It is, arguably, the most important bet humanity has ever made, but it is still a bet. And the evidence, the Hubble tension, the muon anomaly, the measurement problem, the cosmological constant problem, the failure of direct dark matter detection, the persistence of theoretical frameworks that cannot be reconciled, does not yet tell us whether the bet is winning. We are, in the most literal sense, at the edge, standing at the boundary of the known, looking at cracks in the framework, unable to see clearly what lies beyond them, uncertain whether what lies beyond them is a larger and more comprehensive understanding, or something more fundamental and more troubling, the limits of what minds like ours can know. And there is, something in this uncertainty that is not just intellectually interesting but morally significant. Because how you respond to genuine uncertainty, not performed uncertainty, not rhetorical uncertainty, but the real thing, the kind that comes from standing at the edge of what is known and seeing it end, tells you something important about the quality of your thinking. The temptation, when faced with genuine uncertainty, is to resolve it prematurely, to pick the explanation that feels right and hold it as truth, to project confidence where there is none, to mistake the comfortable for the true. This is a temptation that affects scientists as well as non-scientists, experts as well as novices. The history of physics is full of brilliant people who fell in love with an idea and could not let go of it when the evidence moved against it. Einstein himself spent the last 30 years of his life pursuing a unified field theory that went nowhere, refusing to accept the probabilistic interpretation of quantum mechanics that the rest of physics was converging on. His stubbornness was, in retrospect, both deeply human and deeply counterproductive, though perhaps also, from another angle, an example of the dogged persistence that occasionally breaks through to something new. The alternative to premature resolution is not comfortable uncertainty, not a shrug, not an embrace of ignorance as a permanent condition, not the abandonment of the project of understanding. The alternative is what the philosopher and psychologist William James called the will to believe, not belief without evidence, but the willingness to engage with questions at the edge of evidence, to take them seriously, to hold them open, to let them do what serious questions do, change you. When you sit with the question of what dark energy is, or what quantum mechanics means, or whether the universe had a beginning, and you resist the urge to close the question with a convenient answer, whether scientific or theological or simply the comfortable answer of not caring, something happens. The question begins to work on you. It begins to reorganize your sense of what is important, what is known, what is assumed, what is real. And that reorganization is, in its own way, a kind of progress. Not the progress of adding new facts to the stockpile, but the progress of deepening the quality of engagement with reality, of becoming the kind of person who can ask a hard question and sit with it patiently, honestly, without needing it to resolve immediately. That quality of engagement is, in many traditions, considered a form of wisdom. Not wisdom as the possession of answers, but wisdom as the capacity to sustain the right relationship with questions, including the deepest ones, the ones that do not yield to any currently available method. The philosopher Ludwig Wittgenstein ended his Tractatus Logico-Philosophicus with one of the most quoted sentences in the history of philosophy, whereof one cannot speak, thereof one must be silent. He was making a point about the limits of language, about the boundary between what can be said meaningfully and what lies beyond that boundary. Later, in his philosophical investigations, he revised his view of where that boundary lies and how language works. But the underlying insight that there are things beyond the reach of our current frameworks, and that the appropriate response to that boundary is not frustrated noise, but a kind of disciplined attention, remains relevant, perhaps the most relevant thing of all, because the cracks in physics are ultimately cracks in our picture of reality. And our picture of reality is not just a scientific object, it is the foundation on which every other thought we have rests. How you understand the universe, what you think it is made of, whether it is lawful, whether it is intelligible, whether it had a beginning and will have an end, whether consciousness plays a role in its existence. These things shape, subtly and pervasively, how you understand everything else, how you understand yourself, how you understand your relationships and your responsibilities, how you understand the meaning of your own brief, improbable existence in a universe that is mostly dark matter, mostly dark energy, expanding forever at a rate that two different methods of measurement cannot agree on, full of particles whose properties we can calculate to 12 decimal places but whose nature we do not understand, bound together by forces that are almost certainly approximations of something deeper that we have not yet found. The anomalies in physics are not just scientific puzzles, they are invitations. Invitations to take seriously the possibility that the story is not over, that the framework is not complete, that the most important discoveries are not behind us but ahead, possibly ahead in directions that require new concepts, new mathematics, new ways of thinking that do not yet exist, and invitations simultaneously to take seriously the possibility that understanding has limits, not discouraging limits, not limits to be mourned, but limits that are themselves informative. that tell us something about the relationship between mind and reality, that tell us something about what kind of universe this is and what kind of beings we are, that tell us in the most fundamental way possible that we are still, after all this time, at the beginning. The history of science has always been, at its deepest level, a story about the expansion of the human horizon, about pushing outward, past the edge of what was known, into territory that the existing framework said was beyond reach. Copernicus, pushing past the geocentric frame. Newton pushing past the separation of terrestrial and celestial physics. Darwin pushing past the fixed species assumption. Einstein pushing past the absolute frame of Newtonian space and time. Bohr and Heisenberg pushing past the deterministic framework of classical mechanics. Each push required not just new data, but new concepts, new ways of thinking about things that had seemed settled. Each push felt, from within the old framework, like an impossible move, and each push revealed a universe larger, stranger, and more wonderful than the one it replaced. We are at another such moment. The data is in, the anomalies are real, the cracks are structural, and the conceptual push, the new way of thinking, the new framework that will accommodate what the old one cannot, is forming somewhere, perhaps in a paper being written right now, perhaps in an idea that has not yet been clearly stated, perhaps in a combination of insights from physics and mathematics and philosophy and neuroscience and fields that have not yet been defined. The push is coming. It always has. And when it comes, it will not just change physics. It will change everything that physics touches, which is, at the deepest level, everything. But we are not there yet. And in the meantime, there is something valuable in sitting exactly where we are, in the uncertainty, in the aporia, in the feeling of standing at the edge of the framework and looking at the cracks without the comfort of a resolution. Because that feeling, properly understood, properly inhabited, is not a failure of knowledge. It is the precondition for the next expansion of it. You cannot push past the edge if you do not first find it. You cannot revise the framework if you do not first feel its limits. And you cannot feel its limits if you are not paying close enough attention to the anomalies, the discrepancies, the places where the most successful theories in human history quietly whisper that they are not the whole story. The muon wobbles slightly more than the standard model predicts. The universe expands slightly faster than the early universe suggests it should. The equations of general relativity and quantum mechanics refuse to coexist gracefully. The vacuum of space is filled with an energy whose magnitude we cannot calculate and whose nature we do not understand. Dark matter has eluded every detector we have built. The beginning of the universe is beyond the reach of any current theory. And consciousness, the thing doing all this noticing, all this calculating, all this wondering, remains, despite centuries of philosophical inquiry and decades of neuroscientific investigation, one of the most profound mysteries in all of science and philosophy. These are not small things. They are not details waiting to be resolved in the next edition of a textbook. They are the central questions of the most fundamental inquiry humans have ever undertaken, and they are open, genuinely, deeply, possibly permanently open, which means that you, reading this, thinking about this, feeling the slight vertigo of standing at the edge of what is known, are not a passive observer of a process that is already complete. You are a participant in an inquiry that is still in progress. An inquiry that needs not just more data and better instruments, but clearer thinking, deeper conceptual engagement, and the kind of philosophical honesty that is willing to say, we do not know, not yet, maybe not ever in the current form, but we are looking, we are thinking, we are pushing at the edge. And the edge, as always, is where the most interesting things are happening. Consider for a moment what it would mean to genuinely absorb the strangeness of quantum mechanics, not just to know the facts about it, not just to be able to recite the double-slit experiment or define superposition or explain entanglement in broad terms, but to actually feel the conceptual weight of what it implies. The double-slit experiment is the canonical illustration of quantum strangeness, and it deserves to be held in the mind carefully. You fire particles, electrons, photons, even atoms, at a barrier with two narrow slits. On the other side of the barrier, you place a detector that records where the particles land. If you do not observe which slit each particle passes through, the particles form an interference pattern on the detector, a pattern of alternating bands of high and low density that is characteristic of waves, not particles. The particles, each fired individually with long intervals between them, somehow interfere with themselves. Each particle passes through both slits simultaneously as a wave of probability and interferes with itself. On the other side, this is not a metaphor. It is what happens. It has been observed and verified thousands of times with extraordinary precision. But now observe which slit each particle passes through. Place a detector at one of the slits to register which path each particle takes, and the interference pattern disappears. Instantly, completely, the particles begin behaving like classical particles again, going through one slit or the other, landing in two bands on the detector that correspond to the positions of the slits. The act of observation, of gaining information about which path the particle took, destroys the quantum superposition. The particle stops being a wave of probability spread across both paths and becomes a classical particle with a definite location, not because the measuring device physically disturbs the particle in some classical sense. Careful experiments have ruled this out, but because the particle's quantum state becomes entangled with the measuring device, with the environment, with the laboratory, in a way that eliminates the interference. The universe, it seems, has a policy about information. When information about the path of a particle exists somewhere in the universe, when the universe in some sense knows which path was taken, the quantum superposition resolves, the wave function collapses, the probabilities become a definite outcome. What determines which outcome? This is the measurement problem, and it does not have an agreed-upon answer. The Copenhagen interpretation, the most widely taught if not necessarily the most widely believed among working physicists, says essentially that the question is not meaningful. The wave function is a tool for calculating probabilities. The act of measurement produces a definite outcome. Beyond that, asking what is really happening is not a scientific question. This was a pragmatically powerful position when quantum mechanics was being developed. It allowed physicists to use the theory without getting bogged down in philosophical debates that were not yet ripe for resolution. And it remains a valid working stance. But it is profoundly unsatisfying as an account of what is actually happening in the universe. It draws a sharp and unexplained line between the quantum world and the classical world of measurement, without explaining where that line is or why it exists. It treats the observer, the measuring device, the scientist, the consciousness, as something outside the quantum system, immune to quantum rules, when every reason we have tells us that observers are physical systems, and physical systems are quantum mechanical. The many worlds interpretation, developed by Hugh Everett in 1957, takes a different approach. It removes the collapse postulate entirely. The wave function never collapses. It just keeps evolving according to the Schrödinger equation, which is deterministic, linear, and does not produce definite outcomes from superpositions on its own. When a measurement occurs, what happens is not that one outcome is selected and the others are discarded. What happens is that the universe, the entire quantum state of everything, branches. In one branch, the particle went through the left slit. In another branch, it went through the right slit. Both branches are real. Both continue to evolve. The observer in each branch sees a definite outcome, because the observer is also part of the branching universe. And in each branch, there is a version of the observer who sees a different definite result. There is no collapse, because collapse is an illusion generated by the fact that the different branches of the wave function cannot interfere with each other once they have entangled with a macroscopic environment. What looks like collapse from within a branch is simply the fact that you cannot see the other branches. Many worlds is mathematically clean. It requires no additional postulates beyond the Schrödinger equation. It applies quantum mechanics universally without a special role for observers or a mysterious boundary between quantum and classical. And it implies the existence of an unimaginably vast multiverse, an ever-branching tree of quantum histories, each as real as ours, in which every quantum event that could have gone differently did go differently, somewhere in the branching structure. Every measurement, every quantum interaction, every radioactive decay, each one splits the universe into branches. The number of branches is not just large, it is incomprehensibly, unimaginably, perhaps infinitely large. And all of those branches are real, in exactly the same sense that the branch you are reading in is real. You are one version of yourself, in one branch of a vastly branching quantum universe. At every moment, other versions of you are diverging from your history, living out different quantum outcomes, and are as real as you are. This is not science fiction. This is a serious interpretation of quantum mechanics, held by some of the most rigorous physicists alive, and its implications, if it is correct, are staggering. Not just philosophically staggering, not just metaphysically uncomfortable, but genuinely reality-altering in a way that no other scientific idea quite manages to be. Because it means that the universe is unimaginably larger than the observable cosmos. Larger, not in space, but in the number of realized states. It means that every possible quantum outcome is actual. It means that probability, in the physical sense, needs to be completely reconceived, not as the likelihood that a particular thing will happen in a single universe, but as something related to the weight or measure of branches in the universal wave function, a concept that remains technically controversial and philosophically contested. And it means that the universe you inhabit, this specific branch, with this specific history, with the Hubble tension and the muon anomaly and the cosmological constant problem, is one among an unimaginable number of equally real universes, each with its own version of those problems, or no problems, or entirely different anomalies in entirely different physics. The relationship between the many worlds interpretation and the multiverse, suggested by inflation, is one of the more dizzying junctions in contemporary theoretical physics. Inflationary cosmology, the proposal that the very early universe underwent a period of exponentially rapid expansion, is supported by several observational facts, including the large-scale homogeneity and flatness of the observable universe, and the spectrum of fluctuations in the cosmic microwave background. But inflation, taken seriously in its most natural theoretical form, implies that the inflationary process does not end everywhere at the same time. In most of the inflating universe, inflation continues indefinitely. Regions where it ends, where the energy driving inflation converts into the ordinary matter and radiation of a Big Bang, are isolated bubbles in an eternally inflating sea. Each bubble is a separate universe, with potentially different physical laws, different values of the fundamental constants, different amounts of dark energy. Our observable universe is one such bubble, and the collection of all such bubbles, the eternal inflationary multiverse, is the physical counterpart of the quantum branching multiverse of many worlds. Whether these two multiverse concepts are the same thing viewed from different angles, or genuinely distinct proposals, or incompatible alternatives, that is currently an open question without consensus. The multiverse, in either or both of its forms, raises a philosophical problem that is fundamental and fascinating: the problem of fine-tuning. The physical constants of nature, the masses of the fundamental particles, the strengths of the fundamental forces, the value of the cosmological constant, appear to be set to values that allow the existence of complex structures, including stars, planets, chemistry, and life. If any of these constants were even slightly different, if the strong nuclear force were a few percent weaker, if the cosmological constant were a few orders of magnitude larger, if the mass of the electron were significantly different, the universe would be a very different and probably lifeless place. This apparent fine-tuning has been taken by some as evidence for design, for an intelligence that set the constants to values compatible with life. Others have proposed that the constants are what they are because of deeper physical principles that we have not yet discovered, that they are not free parameters, but necessary consequences of a more fundamental theory. And still others have proposed that the multiverse resolves the fine-tuning problem by removing its apparent improbability. If there are an enormous number of universes with different values of the constants, and if we can only exist in universes whose constants are compatible with our existence, then the observation that we live in a fine-tuned universe is not surprising. It is simply the selection effect of being observers in a universe where observation is possible. This is the anthropic principle, and it is one of the most philosophically contested ideas in contemporary physics. Its critics argue that it explains nothing, that saying we observe a fine-tuned universe because we could not exist in a non-fine-tuned universe is circular, vacuous, unfalsifiable, that it is, in the worst sense, a get-out-of-explanation-free card. Its defenders argue that selection effects are real explanatory factors in science, that the anthropic principle is a legitimate application of Bayesian reasoning to cosmological questions, and that dismissing it out of hand is a philosophical prejudice masquerading as methodological rigor. The debate is ongoing. It is intense. And it is a debate in which the boundary between physics and philosophy is not just blurry, but perhaps non-existent. Because whether the anthropic principle is a scientific explanation or a philosophical sleight of hand depends on prior commitments about what explanation means, what counts as a prediction, and what the proper domain of physics is. These are philosophical questions, and they cannot be answered without philosophical thinking. What you are encountering in all of this is a truth about the current state of knowledge that is rarely communicated with full honesty to students, to the public, or even to scientists working outside the specific fields where the anomalies are sharpest. That truth is this: the deepest questions about the nature of reality are genuinely open. Not open in the casual sense of being interesting puzzles that will be solved in the next decade. Open in the deep sense of being questions to which no current framework provides a satisfying answer, and to which even the shape of a satisfying answer is contested. What is dark energy? We do not know. What is dark matter? We do not know, and we have not directly detected it despite decades of searching. Why does the universe expand at the rate it does? We have two measurements that disagree and no explanation for the discrepancy. Why do the fundamental constants have the values they do? We do not know. What does quantum mechanics mean? We have multiple interpretations, each with serious problems, none with consensus. Is there a theory that unifies quantum mechanics and general relativity? We have many proposals, none confirmed. Is there anything beyond the observable universe? We have theoretical reasons to think so, and no way to find out. What is consciousness, and does it play a role in the physical description of the universe? We do not know. This is the honest picture, not a picture of failure. Failure would be a word that misunderstands what is happening. This is a picture of science, at the genuine frontier, doing what science does, which is not having all the answers but asking the questions with the most rigorous tools available. And the most rigorous tools available are, at this moment, not sufficient to resolve the deepest questions. That is not a scandal. It is a situation that calls for more thinking, more creativity, more willingness to question the assumptions built into the current frameworks, more openness to the kind of conceptual revolution that has marked every major advance in physics. But it is also a situation that calls for something beyond physics, because the questions at the frontier are not just technical, they are foundational. They concern the nature of explanation, the nature of reality, the nature of knowledge, the nature of mind. And these concerns require philosophical engagement, not as a supplement to science, not as a comfort when science runs out of answers, but as a genuine partner in the project of understanding. The best scientists working at the deepest levels of physics know this. They read philosophy. They engage with philosophical questions directly, sometimes reluctantly, sometimes joyfully. The best philosophers working at the foundations of science know this too. They study the physics. They engage with the equations, with the experimental results, with the technical literature. The conversation between physics and philosophy at the frontier is not just polite, it is necessary, and it is a conversation that you can join, not by becoming a physicist or a philosopher, though both are worthy pursuits, but by developing the habit of sitting with foundational questions, of asking not just how things work, but what they are, of noticing when an explanation that feels satisfying is actually just familiar, of recognizing the difference between knowing that quantum mechanics predicts the results of experiments with extraordinary accuracy and understanding what quantum mechanics means about the nature of reality, of being willing to say clearly and without embarrassment that you do not know, that the question is hard, that the answer is not yet available, that the strangeness is real and irreducible and deserves to be taken seriously rather than dissolved with a convenient phrase. The Greek philosopher Heraclitus, writing in the 5th century before the Common Era, said that nature loves to hide. He was making a point about the relationship between surface appearances and underlying reality, about the fact that what is most true about the world is often what is least obvious, most counterintuitive, most resistant to easy formulation. The hidden fire he spoke of, the logos, the rational principle underlying the flux and change of apparent reality, was not directly visible. It had to be sought through attention and reason and the willingness to look past what seemed obvious to what was actually there. Modern physics has gone further than Heraclitus could have imagined in uncovering what is hidden, It has revealed that matter is made of atoms, that atoms are made of nuclei and electrons, that nuclei are made of protons and neutrons, that protons and neutrons are made of quarks, that the quarks are held together by the exchange of gluons governed by the strong force, that the entire enterprise of chemistry, every molecule, every reaction, every biological process, is a consequence of quantum mechanical interactions between electrons and atomic nuclei. The layers, though, of hiddenness that physics has uncovered are extraordinary. The distance from Heraclitus to the Large Hadron Collider is a measure of the progress of that uncovering, and yet nature still loves to hide. The deepest layers, the nature of space-time at the Planck scale, the nature of the dark sectors of the universe, the nature of the quantum to classical transition, the nature of consciousness and its relationship to physical reality, remain hidden, not because we have not looked, not because we have not tried, but because the hiding goes deeper than our current instruments and frameworks can reach, and this is not a reason for despair. Heraclitus did not despair at the hiddenness of nature. He treated it as an invitation, a challenge, a reason to look more carefully, think more clearly, question more deeply. The hiddenness was not an obstacle to understanding. It was the shape that understanding had to take. That shape, understanding as a process, as an approach towards something that recedes as you advance, as a relationship with mystery, rather than a conquest of it, is the shape that the deepest scientific and philosophical thinking has always taken. Not the triumphant announcement of final answers, but the patient, rigorous, often humbling pursuit of better questions. Better questions are the product of deeper engagement with the anomalies. Better questions are what the Hubble tension, the muon anomaly, the measurement problem, the cosmological constant problem are demanding. Not just better data, better conceptual clarity about what the data means, what kind of theory it requires, what kind of reality it is pointing toward. Let us think carefully about what kind of reality it might be pointing toward, not to arrive at a definitive answer, that would be premature to the point of absurdity, but to practice the kind of disciplined speculative thinking that the frontier requires. The Hubble tension tells us that the universe is expanding faster than the early universe predicts. What could cause this? One possibility is that dark energy is not a constant, that the energy density of the vacuum is not fixed, but evolves over time, perhaps decaying from a higher value in the past to a lower value now, or interacting with dark matter in ways that affect the expansion rate. Dynamical dark energy, also called quintessence, is a serious theoretical proposal that involves a new scalar field permeating all of space, evolving slowly and driving the acceleration. If this field has slightly different properties than a pure cosmological constant, it could account for the Hubble tension. But dynamical dark energy also raises new questions. What determines the initial conditions of this field? Why does it have the value it does? Why does the energy density of dark energy happen to be comparable to the energy density of matter precisely now, in the current epoch of cosmic history, when for most of the universe's history these densities were wildly different? This is the coincidence problem, and it is almost as vexing as the cosmological constant problem it was meant to address. Another possibility is that the early universe was not quite as the standard model of cosmology describes. Perhaps there was an additional component of energy in the very early universe, an early dark energy, that slightly changed the scale of the sound horizon in the primordial plasma, thereby shifting the interpretation of the cosmic microwave background data in a way that accounts for the discrepancy. This is technically feasible and actively studied, but it requires introducing new physics, new fields, new particles, new interactions, without direct evidence for any of them. It solves one anomaly by introducing new theoretical elements whose own justification remains to be established. This is the nature of theoretical physics at the frontier, solving problems by expanding the framework and then having to justify the expansion. Yet another possibility, one that is more radical and more uncomfortable, is that there is something wrong with how we are measuring distances in the universe. The cosmic distance ladder, which forms the basis of the nearby universe measurement of the Hubble constant, is a chain of methods, each calibrated to the previous one. Cepheid variable stars are calibrated to geometric parallax measurements in the local galaxy. Type Ia supernovae are calibrated to Cepheid distances. Each link in the chain carries its own uncertainties, and those uncertainties compound as you move up the ladder. If there is a systematic error somewhere in the chain, a bias in the Cepheid distance scale, a variation in the properties of type ionosupernovae that has not been fully accounted for, it could produce a spurious offset in the measured Hubble constant. This possibility has been investigated thoroughly by multiple independent teams, and while some sources of systematic error have been identified and corrected, the tension has not gone away. It has, if anything, sharpened as the measurements have improved, but the possibility of an unknown systematic cannot be entirely ruled out, and it is scientifically important to maintain that possibility alongside the more exciting prospect of new physics. The muon anomaly is similarly multi-interpretable. The discrepancy between the measured magnetic moment of the muon and the standard model prediction could be evidence for new particles or forces, a heavy dark sector particle that the muon occasionally interacts with, a new gauge boson, a new scalar field. These possibilities have names and active research programs: dark photons, leptoquarks, extended Higgs sectors. Each is theoretically motivated, each makes specific predictions that current and future experiments could test. But the discrepancy could also be explained by errors in the theoretical calculation of the standard model prediction itself, a calculation of extraordinary complexity that involves summing contributions from hadronic processes that are notoriously difficult to calculate from first principles. Recent independent calculations of these hadronic contributions, using a technique called lattice quantum chromodynamics, have given results that are slightly different from the previous theoretical prediction, different in a direction that would reduce the discrepancy with the experimental measurement. The interpretation of the muon anomaly is therefore genuinely uncertain, not just because the experimental result might change, but because the theoretical prediction against which it is being compared is itself being revised. This is the messy, contingent, deeply human reality of frontier science, not the clean narrative of discovery and confirmation, but the ongoing negotiation between theoretical calculation, experimental measurement, and interpretive framework, all of which are simultaneously in motion. And behind all of this, behind the specific anomalies, the specific tensions, the specific open questions, there is a larger question that all of them are circling, each from a different angle, the question of what the universe is made of, at the most fundamental level, not just what particles exist, what forces act, what fields permeate space, but what the deep structure of physical reality is, whether space-time is continuous or discrete, whether the universe is fundamentally quantum mechanical, or whether quantum mechanics is an approximation to something deeper, whether the laws of nature are truly universal, the same everywhere and every when, or whether they are local expressions of more complex underlying structures that vary across the multiverse, whether information is the fundamental currency of the universe, whether the physical world is, at its deepest level, informational rather than material, built not from stuff, but from bits. This last possibility, the idea that information is more fundamental than matter or energy, has been gaining traction in theoretical physics for several decades. It traces its roots to John Wheeler's late career work, captured in his phrase it from bit, the idea that every physical entity, every particle and field and interaction derives its existence from answers to binary questions, from information. In Wheeler's vision, the universe is not made of stuff that happens to carry information. The universe is made of information, from which the appearance of stuff emerges. This is a radical proposal, and it remains speculative, but it has found unexpected support from the study of black holes and the thermodynamics of space-time. When Stephen Hawking showed, in 1974, that black holes radiate, that quantum effects near the event horizon cause black holes to emit thermal radiation and gradually evaporate, he created one of the deepest puzzles in theoretical physics. Because the radiation that comes out of a black hole is thermal, it carries no information about what fell in. If a star collapses to form a black hole, and then the black hole evaporates, the information about the quantum state of the original star appears to be lost. It is not encoded in the outgoing radiation. It is simply gone. But quantum mechanics, in its standard formulation, says that information cannot be destroyed. The evolution of quantum states is unitary, which means it is time reversible, which means the information about the initial state is always preserved in the final state, even if in a scrambled and inaccessible form. The apparent destruction of information by black holes The black hole information paradox is a direct conflict between Hawking's semi-classical calculation and the fundamental principles of quantum mechanics, and it has not been resolved. Not fully, not in a way that has achieved consensus. The most popular proposed resolution, developed in the context of string theory, is black hole complementarity and the holographic principle. So, holographic principle, inspired by work of Gerard 't Hooft and Leonard Susskind, proposes that the information content of a region of space is not proportional to its volume, as you might expect, but to its surface area. That the three-dimensional world inside a black hole is, in some deep sense, encoded on the two-dimensional surface of its event horizon. That the universe itself might be holographic. That three-dimensional physical reality is a kind of projection from a lower dimensional surface at the boundary of the universe. This idea received extraordinary mathematical support from the discovery, by Juan Maldacena in 1997, of what is called the AD-S-CFT correspondence, a precise mathematical equivalence between a theory of gravity in a certain type of curved spacetime and a quantum field theory without gravity on the boundary of that spacetime. The correspondence is exact and has been verified in thousands of calculations. It demonstrates, at least in a specific mathematical setting, that gravity and quantum mechanics can be reconciled, that a theory of quantum gravity exists, at least in this particular geometry, and it suggests that spacetime itself, including gravity, might emerge from the quantum entanglement structure of a boundary theory. That space is not fundamental, that it is emergent, that the three-dimensional world you inhabit is a kind of hologram, a projection from quantum information on a lower dimensional surface. This is one of the most extraordinary ideas in the history of physics, and it is deeply uncertain. The AD-CFT correspondence works in anti-de Sitter space, a spacetime with a negative cosmological constant, which has very different properties from the spacetime we actually live in, which has a positive cosmological constant. Whether the holographic principle applies to our universe, and if so, in what form, remains an open question. Whether spacetime is genuinely emergent from entanglement, or whether the mathematical duality of AD-CFT is a tool for calculation rather than a description of the real structure of reality, is philosophically contested. Whether the information paradox is actually resolved by the holographic principle, or whether it remains open despite the appearance of resolution, is technically debated, and yet, even in its uncertain, contested preliminary form, the emergence of spacetime from quantum information is one of the most promising directions in current theoretical physics. It connects the quantum foundation's questions to the cosmological questions to the black hole questions in ways that suggest they are not separate problems, but different faces of the same deep mystery. The mystery at the center of all of this, the thing that all these different anomalies and proposals and frameworks are circling, might be stated this way. We do not understand the relationship between the quantum and the classical. We do not understand why the quantum world, with its superpositions, its entanglement, its non-locality, its irreducible probability, gives rise to the classical world of definite objects, definite locations, definite causal sequences. We do not understand why the world of ordinary experience, which is described so well by classical physics and classical logic, emerges from a quantum substrate that violates every intuition that ordinary experience generates. We have a technical explanation: decoherence, the entanglement of quantum systems with their environments, which suppresses the interference effects that manifest quantum behavior. But decoherence is not the same as collapse. It explains why quantum superpositions become practically invisible at macroscopic scales. It does not explain why one definite outcome occurs rather than another, or whether in some deeper sense all outcomes occur. The measurement problem survives decoherence, and without a solution to the measurement problem, we do not have a complete theory of quantum mechanics. We have an extraordinarily successful algorithm for predicting experimental results, built on a foundation that we do not fully understand. There is something almost comic about this situation when you step back far enough to see it clearly. Humanity spent millennia building tools to understand the world, from the first stone axe that required an understanding of material properties, to the bronze casting techniques that required an understanding of metallurgy, to the steam engine that required an understanding of thermodynamics, to the transistor that required an understanding of quantum mechanics. Each step in this progression involved deeper understanding of the underlying physics, and that deeper understanding enabled more powerful technology. The transistor, the basic unit of all modern computing, the device that makes smartphones and laptops and the internet possible, operates entirely on quantum mechanical principles. Its behavior cannot be explained by classical physics. It is the most direct product of quantum mechanics in everyday life, and it was built by people who did not, and do not, fully understand what quantum mechanics means. They understood it well enough to predict its behavior, to calculate its properties, to engineer its function. But the question of what is actually happening in a quantum system, what reality looks like at the quantum level, what it means for an electron to be in a superposition, what actually occurs when a measurement is made, remains unresolved. We built the information age on a theory whose meaning we do not understand. That is extraordinary. That is also, in a quiet way, terrifying. Not terrifying in the sense of suggesting that the technology is unsafe or that the predictions are unreliable. Terrifying in the sense of revealing how shallow our understanding can be even at its deepest. Terrifying in the sense that it forces a confrontation with the possibility that understanding is not a monolithic thing, that you can understand how without understanding what, that predictive power and explanatory depth are not the same thing, that a framework can be extraordinarily successful while being, at its foundation, conceptually incomplete. This distinction between predictive success and explanatory completeness is one of the most important distinctions in the philosophy of science, and it is one that gets lost in the enthusiasm of technological progress. Progress feels like understanding, but it is possible to make progress without understanding. It is possible to find the right equations without knowing what the equations are equations of. Newton found the right equations for gravity without knowing what gravity was. He could calculate the orbits of planets, the trajectories of cannonballs, the behavior of tides with extraordinary precision. He explicitly refused to hypothesize about the mechanism of gravity. His famous phrase, hypotheses non fingo, I feign no. Hypotheses was a methodological position, not just a rhetorical one. He knew that his equations worked. He did not know why they worked, what gravity actually was, how it could act across empty space without any medium of transmission. It took Einstein, more than 2 centuries later, to provide the conceptual framework that explained why Newton's equations worked in the domain where they worked, and where and why they would fail. The explanation came long after the prediction. Understanding lagged behind calculation by 200 years. We may be in a similar situation with quantum mechanics. The calculation works, the explanation is still coming. But here is the deepest version of the question. What would an explanation look like? What would it mean to explain quantum mechanics, Q? Not just to use it, not just to refine it, not just to find the correct interpretation among the available options, but to genuinely explain why the world at the quantum scale behaves the way it does. This question assumes that quantum mechanics requires explanation in a deeper sense, that it is not just a brute fact about reality, a fundamental description that accepts no further analysis, but rather a consequence of something more fundamental that we have not yet identified. That assumption is itself philosophical. It is the assumption that understanding always requires going deeper, that explanation is always reduction to more fundamental constituents or more fundamental laws, and that assumption might be wrong. Perhaps quantum mechanics is irreducibly strange. Perhaps there is no deeper theory of which it is an approximation. Perhaps the weirdness is all the way down. The universe might simply be quantum mechanical, and that might just be how it is without any further story to tell about why. If that is the case, if quantum mechanics is fundamental and irreducible, then the project of explanation in physics has a terminal point, and we may already be close to it. Not close in the sense of having solved everything, but close in the sense of having identified the framework within which everything occurs, without necessarily being able to explain why the framework is what it is. This is a genuinely possible outcome of the inquiry. It is an outcome that many physicists implicitly accept when they dismiss the measurement problem as a pseudo-problem and insist that shut up and calculate is the appropriate response to foundational questions, not because they think the questions are unimportant, but because they think they are unanswerable, because they believe that at some level, you simply have to accept the rules of the game and stop asking why the game has those rules. The philosopher Bertrand Russell, reflecting on the nature of causal explanation, pointed out that every explanation requires assumptions, premises that are themselves unexplained. You explain a phenomenon by showing that it follows from more general principles, but those more general principles are themselves unexplained. You can always ask why, and at some point you reach bedrock, a place where further explanation is not available. Russell was drawing a general logical point, not a specifically physical one, but it applies to physics with particular force. Every physical theory rests on assumptions, axioms, postulates, empirical regularities treated as fundamental, that are not themselves derived from anything more fundamental. The laws of physics are not explained by physics. They are assumed by physics. Whether they can be explained by anything at all, whether the question of why the laws are what they are has an answer, is one of the deepest questions in the philosophy of nature. The physicist Lee Smolin has argued that the laws of nature themselves might evolve, that what we call the laws of physics are not eternal truths, but regularities that emerged and continue to evolve over the history of the universe, perhaps through a process analogous to natural selection. In Smolin's cosmological natural selection proposal, universes give birth to new universes through the formation of black holes, and the new universes inherit slightly modified physical constants from their parent universes. Universes with constants that favor the production of black holes, and hence more offspring universes, become more common over time. Our universe, with its particular values of the physical constants, would be explained not by fine-tuning or by a multiverse of simultaneously existing universes, but by an evolutionary process that selects for universes that are good at reproducing. This is a fascinating idea. It is also essentially untestable, at least with any technology currently conceivable, and it raises the question of what the meta-laws are, the laws that govern how laws evolve, and whether those meta-laws are themselves subject to evolution, and so on. The regress of explanation does not obviously stop. Perhaps the most honest and most radical position is the one taken by some philosophers of physics who argue that the question of why the laws are what they are may not have an answer, not because our knowledge is limited, but because the question is malformed. The laws of physics are what they are. There is no further fact about why they are that way, any more than there is a further fact about why the number 7 is prime. 7 is prime because of what 7 is and what primeness is, and there is no deeper explanation available. The mathematical structure of the universe is what it is. The laws are what they are. The constants have the values they have. And the project of explanation terminates not in a grand unified theory that explains everything, but in the recognition that some things are simply the case without any further story to tell. This position is sometimes called the brute fact view of natural law. It is philosophically austere. It offers no comfort to those who want a reason behind the reasons, a cause behind the causes, a purpose woven into the structure of things. But it is honest, and honesty, at the frontier of knowledge, is more valuable than comfort. The universe may simply be the way it is, without explanation, without purpose, without any deeper story. The laws may be brute facts. The constants may be brute facts. The existence of anything at all, the most ancient and most vertiginous of all philosophical questions, the question Leibniz posed when he asked why there is something rather than nothing, may admit of no answer, not because the answer is hidden, but because the question assumes a framework of explanation that does not apply to existence itself. Why is there something rather than nothing? This is a question that physics cannot answer, not because physics is incomplete, though it is, but because the question precedes physics. Any physical answer to the question assumes the existence of physical laws, physical fields, physical structures. It assumes the very thing it is trying to explain. You cannot explain why there is something rather than nothing by appealing to quantum vacuum fluctuations, because a quantum vacuum is not nothing. It is a physical system with specific properties, governed by specific laws. You cannot explain it by appealing to the laws of mathematics and their necessary existence, because that assumes that mathematical necessity is a kind of existence, which is precisely what is at issue. You cannot explain it by appealing to a creator, because a creator is something, and the question of why there is something rather than nothing applies to the creator as much as to anything else. Every proposed answer to the question either assumes what it is trying to explain, or terminates in the same brute fact that the question was trying to avoid. This is not a failure of imagination. It is not a gap that more knowledge will fill. It is a structural feature of the question. a question that resists every form of explanation because explanation itself is something, and the question is about why there is anything at all. It is, in the strictest philosophical sense, the deepest question, and it is one that has not moved perceptibly closer to resolution in 3,000 years of philosophical inquiry or 300 years of scientific investigation. The brute fact of existence remains a brute fact. The mystery remains a mystery, and the appropriate response to it, the response that philosophy, at its best, has always recommended, is not to dissolve it with a clever argument or a reassuring narrative, but to sit with it, to let it do what it does to a mind that takes it seriously, to open that mind, to loosen its grip on the things it thought it knew, to make it more attentive, more humble, more genuinely curious about the extraordinary improbability of there being anything to be curious about, because you are something rather than nothing. You are a physical system of extraordinary complexity, made of particles that obey quantum mechanical rules, organized into atoms and molecules and cells and organs and nervous systems, generating, somehow through processes we do not understand, the experience of reading these words, of following these arguments, of feeling the slight vertigo of standing at the edge of the knowable. You are a part of a universe whose dominant constituents are invisible to you, whose rate of expansion cannot be agreed upon by the best measurements available, whose quantum foundation cannot be reconciled with its gravitational structure, whose beginning is beyond the reach of current theory, and whose ultimate nature is the subject of frameworks that are each incomplete in their own way. You are made of stardust. The heavier elements in your body were forged in the cores of stars that lived and died before the sun existed, and you are held together by forces whose ultimate description is one of the greatest unsolved problems in physics. You are, in the most literal sense, a part of the universe that has become capable of wondering about the whole. That is not a small thing. In fact, from a certain angle, it is the most extraordinary thing in the universe. More extraordinary than dark energy. More extraordinary than quantum entanglement. More extraordinary than the first moments after the Big Bang. That matter, organized in a particular way, can turn and look at itself and ask what it is, can generate the experience of inquiry, the experience of confusion, the experience of wonder, is a fact that no current theory explains and that every current theory must eventually reckon with. Consciousness is not a peripheral phenomenon. It is not a side effect. It is the precondition for everything else in this conversation. Without consciousness, there is no observation, no measurement, no science, no philosophy, no question, and no answer. Consciousness is not just something to be explained by physics. It is the thing doing the explaining. And the fact that it remains unexplained, that after centuries of philosophical inquiry and decades of neuroscientific research, the hard problem of consciousness remains hard, remains unresolved, remains a genuine mystery, is perhaps the most important and most neglected anomaly of all. The hard problem of consciousness was given its name by philosopher David Chalmers in the 1990s. It is the problem of explaining why physical processes in the brain give rise to subjective experience, to the felt quality of experience, what philosophers call qualia. Why does the processing of visual information in the brain produce the experience of seeing red, rather than just the functional response to a particular wavelength of light? Why is there something it is like to be you, to feel, to perceive, to think, rather than just an information processing system operating in the dark, functionally equivalent, but experientially empty? The easy problems of consciousness, explaining how the brain integrates information, directs attention, controls behavior, produces reports of mental states, are difficult in a scientific and technical sense, but they are problems that, at least in principle, yield to the methods of neuroscience and cognitive science. The hard problem is different in kind. Even a complete functional account of the brain, a complete description of every neural process, every information integration, every computational transformation, would not by itself explain why any of it is accompanied by subjective experience, why there is experience at all, why the lights are on. The hard problem matters for physics not just as a philosophical puzzle, but as a potential constraint on physical theory. If consciousness is not reducible to physical processes, if there is something about subjective experience that cannot be fully captured by any physical description, however complete, then physics, as a project of describing reality, is incomplete in a way that is more fundamental than the Hubble tension or the muon anomaly. Those anomalies are gaps in the current theories. The hard problem, if it is real, is a gap in the entire project of physical explanation. It is the suggestion that physical description, however detailed and comprehensive, leaves something out, that the felt quality of experience is not captured by any third-person, objective mathematical description of the brain or any other physical system. And if that is right, then the universe contains something that is not physical, or the concept of physical needs to be expanded in ways that current physics does not accommodate. Or the hard problem is a pseudo-problem generated by a confusion about the nature of explanation. Each of these options is radical. If consciousness is genuinely non-physical, that has implications for the completeness of physics as a description of reality that are almost too large to contemplate. If the concept of physical needs to be expanded to include consciousness, if consciousness or experience is a fundamental feature of reality, as panpsychist philosophers like David Chalmers and Philip Goff have proposed, then the ontology of physics needs to be completely reconceived. And if the hard problem is a pseudo-problem, if the felt quality of experience is somehow, despite appearances, fully explained by physical processes, and our sense that it is not, is a cognitive illusion, then we need a very good account of why such a systematic and compelling illusion arises, and that account is not currently available. The panpsychist option deserves a moment of attention because it is gaining traction in serious philosophical circles in a way that it has not since the early 20th century. Panpsychism is the view that consciousness or experience is a fundamental feature of reality, present at all levels of physical organization, not just in complex nervous systems, but in simpler systems, perhaps in all physical systems, perhaps in matter itself. Not that electrons have rich inner lives or that rocks are sentient in any meaningful sense, but that there is some form of proto-experiential property, some primitive form of what it is likeness, at the most fundamental level of physical reality, and that the rich conscious experience of humans and animals is composed of and built up from these primitive properties. Panpsychism was held by Spinoza, by Leibniz, by William James, by Alfred North Whitehead. It fell out of fashion in the 20th century as scientific materialism became the dominant framework, but it has returned, not as mysticism, but as a serious philosophical response to the hard problem. Because if consciousness cannot be explained by physical processes, and if consciousness clearly exists, if the felt quality of experience is real, as it evidently is, then either physics is incomplete, or the boundaries of the physical need to be redrawn to include experience as a fundamental feature. This is, in a sense, the mirror image of the problem in physics. In physics, the anomalies suggest that the physical world is larger, stranger, and more complex than current theories describe. In philosophy of mind, the hard problem suggests that reality is larger, stranger, and more complex than a purely physical description can capture. Both problems point in the same direction, toward a more expansive and more honest account of what reality is, and the account that does not prematurely foreclose the strangeness, that does not pretend to know more than it does, that takes seriously the full weight of what the evidence, both experimental and philosophical, is demanding. It is possible that the resolution of the hard problem and the resolution of the crisis in physics are connected. Some physicists and philosophers, including Penrose and the late David Bohm, and more recently physicist Carlo Rovelli and philosopher Thomas Nagel, have suggested in different ways and with different degrees of development that the incompleteness of physics and the mystery of consciousness might be symptoms of the same underlying inadequacy, that the third-person, objective, mathematical framework of physics might be missing something that the first-person reality of experience is directly revealing, that the split between observer and observed, which is the split that creates the measurement problem in quantum mechanics, the split that makes the hard problem hard, might be artificial, might be a feature of our conceptual framework rather than a feature of reality, and that a more adequate framework might dissolve both the measurement problem and the hard problem by reconceiving the relationship between the observer and what is observed, between consciousness and the physical world, between the map and the territory. This is speculative. It is not established science. It is not established philosophy. It is the frontier of both, the place where the most ambitious and the most careful thinkers are reaching towards something that does not yet have a clear form. And that is exactly where this conversation belongs. Not because speculative ideas are always right, they are usually wrong, but because at the genuine frontier, the alternative to speculation is silence. And silence, in the face of genuine questions, is not wisdom. It is abdication, the willingness to speculate carefully, to hold possibilities open, to follow implications, to take seriously ideas that seem strange precisely because they are strange in the right direction, is a crucial intellectual virtue, distinct from credulity, which accepts ideas without adequate reason, distinct from dogmatism, which holds ideas without openness to revision, but also distinct from the false humility of refusing to engage with ideas that lack full empirical support. Science has always advanced through ideas that, at the time of their proposal, had more theoretical motivation than empirical confirmation. General relativity was proposed before any of its major predictions were confirmed. The Higgs boson was predicted 48 years before it was found. The existence of antimatter was predicted by Dirac's equation before it was detected. Speculation, disciplined, mathematically grounded, philosophically aware speculation, is not the opposite of science. It is its seedbed, and the seedbed right now is extraordinarily fertile. Precisely because the anomalies are real, the frameworks are strained, and the next big idea has not yet arrived. What will that idea be? Honest answer, we do not know. No one knows. If we knew, it would already be the idea. But we can say something about what kind of idea it will likely need to be. It will need to reconcile quantum mechanics and general relativity, to produce a theory of quantum gravity that reduces to both in their respective domains and resolves their conflict in the extreme, conditions where both are relevant. It will need to explain the value of the cosmological constant, or to explain why the current framework for calculating it is wrong and what the correct calculation looks like. It will need to account for the Hubble tension, either by identifying the systematic error in one of the measurements, or by introducing new physics that modifies the expansion history of the universe in the right way. It will need to make sense of dark matter and dark energy, either by identifying them directly or by providing a modified framework in which they are not needed. It will need to address the measurement problem, either by providing a rigorous derivation of the classical world from quantum mechanics, or by revising quantum mechanics in a way that makes the derivation unnecessary. And it will need to do all of this while remaining consistent with the extraordinary precision with which current theories predict experimental results. That is an extraordinarily tall order. It is arguably the most challenging intellectual problem humanity has ever faced, and it is the problem that the most creative and rigorous minds of the coming generations will spend their lives on. You might be one of them, not necessarily as a physicist or a philosopher, though those are among the finest things a person can choose to be, but as someone who takes the question seriously, as someone who has felt the vertigo of standing at the edge of the known and looked, honestly, and without flinching, at the cracks in the framework, as someone who understands that the most important intellectual activity is not the accumulation of established knowledge, essential as that is, but the cultivation of the capacity to engage with the unknown, to hold questions open, to tolerate uncertainty, to follow an argument wherever it leads, even when it leads into territory that the existing framework cannot accommodate, to distinguish between the comfortable and the true, and to choose the true even when it is uncomfortable. That capacity, the capacity for genuine intellectual engagement with genuine uncertainty, is not something that physics or philosophy can give you directly. It is something that physics and philosophy at their best can cultivate. They can cultivate it by showing you what the real questions are, by giving you the tools to think about them rigorously, by showing you what careful thinking looks like, what intellectual honesty looks like, what the difference is between a question that is hard and a question that is answered too quickly, by showing you that the universe, this extraordinary, improbable, mostly dark, rapidly expanding, quantum mechanical, possibly holographic, definitely strange universe, is not a problem to be solved but a reality to be engaged. A reality that is larger than any framework we currently have to describe it. A reality that is asking, through its anomalies and its cracks and its whispered suggestions of something beyond the current edge, for a larger and more honest kind of thinking than the one we currently have. The universe is not finished with us, and we are not finished with it. The inquiry continues. The anomalies accumulate. The frameworks strain and occasionally crack. And somewhere in the interplay between precise measurement and deep conceptual thought, between the evidence that the instruments give us and the frameworks that our minds construct to make sense of it, between the humility of acknowledging what we do not know and the ambition of refusing to stop looking, somewhere in that interplay, the next understanding is forming, slowly, imperfectly, through the combined effort of thousands of minds working at the edge of what is knowable, arguing and calculating and measuring and revising, and sometimes, in moments of extraordinary clarity, seeing something that was not visible before, something that makes the anomaly make sense, something that makes the crack not a weakness but a window. We do not know what is on the other side of the window. That is the most important thing you can take from this conversation. Not a set of facts about the Hubble constant or the muon anomaly or the cosmological constant, though those facts are important and worth knowing. But the deeper thing, the recognition that genuine knowledge includes the knowledge of its own limits, that the most educated response to the deepest questions is not a confident answer, but a refined appreciation of how hard the questions are. That standing at the edge of the known and feeling the vertigo is not a failure of understanding, it is the beginning of it. The ancient Socratic tradition held that wisdom begins with the recognition of ignorance, that the examined life, the life of genuine intellectual engagement, starts not with the accumulation of answers, but with the honest confrontation of questions. Not fake humility, not the performance of uncertainty, but the genuine recognition that the things worth understanding are hard, that easy answers are usually wrong, and that the discipline of sitting with difficulty, of maintaining attention and rigor in the face of genuine mystery, is the highest form of intellectual engagement. That tradition is not outdated, it is not superseded by science. It is in fact what science at its best embodies: the refusal to accept comfortable explanations, the commitment to following evidence wherever it leads, the willingness to revise even the most deeply held frameworks when the evidence demands it. The crisis in physics is, in this light, not a crisis in the pejorative sense. It is the crisis of a discipline at the edge of its current reach, straining toward the next expansion, feeling the limits of its current tools and generating the kind of productive tension that has always preceded the most important advances. The cracks are real, the anomalies are real, the uncertainty is real, and so is the extraordinary tradition of inquiry, stretching from the first person who looked up at the night sky and wondered what it was, through every generation of thinkers who refused to accept easy answers, to the physicists and philosophers and mathematicians working right now at the most demanding frontier of human knowledge. That has brought us to this point, a point where we know that the universe began approximately 13.8 billion years ago in an event of extraordinary density and temperature, a point where we know that galaxies are receding from us at rates that increase with distance, driven by an energy we cannot identify, a point where we know that the matter we can see represents only 5% of the total mass energy content of the universe, a point where we know that the particles that make up that visible matter obey rules that are so strange, so counterintuitive, so thoroughly alien to the experience of living in the medium-sized world, that a century of effort has not produced consensus on what those rules mean about the nature of reality, a point where we know that the two greatest theories in the history of physics cannot be combined, a point where we know that the beginning of the universe is beyond the reach of any current theory, a point where we know that consciousness, the very thing that knows all of this, is not understood. We know an extraordinary amount, and we stand at the edge of what we know, looking into what we do not know, aware that the edge is not a boundary but a beginning, that the darkness beyond the framework is not the absence of reality, but the presence of more reality than the framework can currently contain, that the anomalies are not embarrassments but invitations, that the cracks are not failures but opportunities, and that the most important thing any mind can do, confronted with the genuine frontier of knowledge, is to stay, to not flinch, to not retreat into the comfortable territory of what is already known, to not pretend that the questions are answered when they are not, to stay at the edge, to keep looking, to keep thinking, and to hold open the possibility that what lies beyond the current framework is not just more of the same, but something genuinely new, something that will change not just what we know but how we think, not just the content of our understanding, but its form, not just the equations, but the concepts, not just the models, but the very idea of what a model is and what it means to understand. That is the invitation that the universe is extending, through its anomalies and its cracks, through its dark sectors and its quantum strangeness, through its expanding, accelerating vastness, and its irreducible weirdness at the smallest scales. An invitation to think harder, more carefully, more honestly, and more humbly than has been necessary before. An invitation to step into the genuine unknown, not the comfortable unknown of problems that are merely unsolved, but the deep unknown of questions whose very framing may need to be reconceived. An invitation to be, in the most serious sense, a student, not of what is already known, but of what is not yet known, not of the answers, but of the questions, not of the framework, but of its limits, and in those limits perhaps of something larger, something that the current frameworks are gesturing toward but cannot yet contain, something that the universe, in its patient and indifferent and extraordinary way, is slowly, through the accumulation of anomalies and the persistence of mysteries, trying to tell us, whether we are capable of hearing it, whether minds like ours, built by evolution for a purpose entirely different from cosmic understanding, equipped with mathematics and instruments and philosophical traditions that are extraordinary but finite, standing in one small corner of one ordinary galaxy in one improbable universe, whether we are capable of hearing what the universe is trying to tell us is itself one of the deepest open questions, and the only way to find out is to keep listening.